Good morning, everyone. I hope you're all doing fantastic this morning. Let me just share my stream. Oh, that's very loud. Let me just lower that for you guys. Sorry about the blasting of music in your ears. Anyway, so we're going to go after it today. We're going to go pretty hard on the filament stuff. I have to admit, yesterday I could have worked harder. Let me just get Toggle Track open, my tracking app, and I realized that I don't know why, I just feel like yesterday I just kind of pulled back on the accelerator when it comes to, you know, working hard and stuff. Like literally we're just under 2 hours here, and that was despite learning what ambient occlusion was after the stream. This is not acceptable. We need to be working harder than that. So we're going to be doing the same as what we did yesterday, but what I'm gonna do is I'm gonna make it so I'm gonna do more studying than more. Yeah, let me just get up the chat. More studying than writing code. The problem is right now is I'm in this position where I should just blast through this all the maths to do clear coat, to do cloth, because more importantly than any of this, and anisotropy after cloth, blah 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 blah, is the lighting stuff. Like, this is more important. I can have the nicest BRDF in the world. If I have one light source, then I have one light source, right? So we need to figure out like how to do this stuff. All graphics programmers can do this. I'm behind when it comes to them. So I need to get better. I can't accept my current level of ability, and I can't accept working only 3 hours on a project. So we got to step it up a bit today. So I'm gonna be a bit harsh on myself and make sure that, one, I stick to what I'm doing, and two, I don't flounder around. So hopefully you're here for it. The idea anyway is to get through as much of this as possible. I really want today, my goal is to finish this. If I don't achieve it and I get very close, that'll be also fine. But in the stream, we are on where are we? We got to here, right? So there's tons of stuff to do before we get to lighting. I can't afford to spend, you know, weeks and weeks and weeks just going through this bit one thing at a time, you know. So going to be less programming today, more studying. The great lock-in has occurred, as the kids would say, or something. Anyway, obviously I'll still read chat and stuff. That's a given. If you guys want to you know, ask any questions about stuff or want me to demonstrate anything, I will. I'll obviously help anyone out who wants stuff help. You know, you want things helped out in chat, that's also fine. But for the most part, we've just got to drill this in. I think I split this up on purpose, yes. So, oops, didn't mean to do that. So let's start the timer. Yes, we want to get back to you know at least 7 hours today is going to be the minimum. Do you need those things you said? If not, you can do it later. For me, it's like I want to know them more than. You are right. I maybe should think about the order at which I do these things in. No, it's fine. I just need to work harder. I just need to delete row. I just need to go fast, and then it's a non-issue. If you know what I mean, right? If I just get it done and don't have to worry about it, they're not required. No, I'm gonna have them in. Maybe anisotropic on like metal would be good. Clear coat, but maybe in a niche situation, but cloth probably not. So yes, if I just go fast, then I don't have to worry about this anymore, you know. So I'm going to say reflectance, because what I really need to get to is light clustering. So I'm just going to go quick today. Okay, so hello, very early stream. Yes, we're back to what we should be doing. Early streams. I should be pushing myself. Anyway, so for people who are tuning in for the first time, this is the filament documentation. We have a ton of stuff to learn from this renderer, and through reading the maths and like maybe doing a tiny bit, I'm going to try to avoid this, but some my point is not adding features to your BRDF you don't need. I think what I'm going to do is just not, I'm going to add them in, right, Ratchet, and not use them, which is going to seem counterintuitive, but I want this lighting to be the whole point of writing this engine is the space game is going to be like the base of like what other games I want to write with this engine. So it's not like I'm going to write this BRDF and then just, you know, make space games forever. So I might want to add cloths. That sounds like a lot of bloats. So I'm going to if-def them out, I think. Okay, let me think about this then. I do respect your opinion, so let me think about this a bit. Okay, so the opinion of Ratchet, which I do respect, is that if I'm making a space game, then I don't need cloths. Like I don't need this for the BRDF in the BRDF calculation. It just increases the complexity of the BRDF, and the downside of that is it can be slower if I have all this like multiplied together to finally create the regular bidirectional reflectance distribution function, which is what this is part of the lighting equation. So that would require kind of like a potential downside is that one, I don't have for clear coat, for example, I do not have the parameters supported. And even if I learn all the maths, then the clear coats. Okay, so I think, let me think about this, because I was just like, let's just go through it all, I don't care. But there is a way, there is this concept called being a busy idiot, where you're working hard on the wrong thing, and there is I've got to be careful of that as well. So let me, because I do respect people's opinion in chat. Not always, but Ratchets I do. Okay, so is there any, like, how in depth do I need to go? That's the question. So if I have a huge BRDF that goes on and on and on and does a bunch of stuff, and I do, for example, this thing, which is like the D part of the normal distribution function in GLSL, I've increased the complexity of the calculations per pixel, and that might slow things down. And it's also possible that I wouldn't want this for every single material. I would need this for only for cloths. So it would be like I need a separate renderer for cloths or something like that. For example, like this, like cloth distribution. You know, this has a cloth. This has a whole cloth setup, right? And then it has a, yeah. So this seems like its own renderer. Sorry, its own BRDF calculation. Okay, let's keep working through this. There is also a Birdian's ass. What's that mean, Mado? Actually don't know what that means. Is that the same thing as being a busy idiot? Where you're just kind of you're just putting burden on on a donkey for no reason. or something like that. Carrying weight for no reason kind of thing. Okay, so let me just go through. All right. The donkey's dilemma got you. Thank you. This is also work, by the way. I don't mind. I don't mind thinking through what is necessary to learn, especially at the beginning of the stream. So that's fine. I don't mind doing this. This is completely chill. So we do have anisotropic lighting, which it looks like it extends the smith. So I'm just gonna be careful here what I think I need to do, especially in my space game with like basically no metal anyway. Okay, so I don't mind learning that one. That one's fine. This is fine. Well, you need a separate BRDF for clear coats. Well, you really need a separate BRDF for clear coats, anisotropic materials. You need a separate one, really? You can't combine. So clear coats, yeah, it looks like the calculation is different here, but you can't combine these two together. Interesting. Let me look through. In that case, yeah, I might just do lighting then, and we'll blast through as much lighting as we can because we need to get to light clustering at some point in the future. Okay, so yes, I have less information than some people in the chat, so sometimes I might not make the best decisions. So let's keep thinking for a minute. All right. Let's see. So I would need a 3 different. Let's see. Yeah, because I do need to be careful here. If I make a render at like, this is cool. But if it's only 4 conductors, and it's only 4, and it's like no one's gonna really notice. Not that it's not. Let me just look. I just want to see if this is not. Okay, so straight off the bat, I'm going to say we're going to skip cloths at the very least. No further remapping required. Okay, so what I'm going to do is just see. Okay, the standard model described previously can only describe isotropic surfaces that whose properties are identical in all directions. Many real-world materials, such as brushed metals, can, however, be replaced using the anisotropic model. Okay, comparing isotropic for BRDF, so clear coats, cloth, anisotropic, and standard. He is both thirsty and hungry, and each is in place. Ace is placed on the other side of the room, so he ends up dead because he can't pick what he wants to do first. Yes. Paralysis of choice. I see what you're saying there with the paralysis of choice. Yeah, okay, so what we're going to do then is blast through the anisotropic and just see if we actually need it, okay? I'm not going to write any notes, I'm just going to read it. Okay, so 4.10.1, anisotropic speculated BRDF. The isotropic speculated BRDF described previously can be modified to handle anisotropic materials. Barely achieved this by using an anisotropic GGX NDF. Okay. The normal distribution function unfortunately relies on 2 supplemental roughness terms, noted as alpha B. The roughener alongside the bidirectional roughness along bitangents direction, and AT roughness along the tangent direction. Okay, so I do have bitangents and tangents, but I don't have roughness relative to those. So yes, we're gonna. This is not, I don't think, doable. unless I figure out how to work out what the roughness direction would be on the fly in the shader. Okay, so Nobel and proposed a way of doing A, B, and AT using anisotropy parameters that describe the relationship between the two roughness values for material. Okay, so we have A is AT and B is alert between those two minus the anisotropy variable, which I don't exactly have. The relationship defined is different and offers more pleasant intuitive results, but is slightly more expensive. Okay, so alpha, so that alpha is roughness, right? 1 times by this anisotropy, and then, okay. And then the square root, okay. We instead opted to follow the relationship in Kulia, created a sharp highlight. Okay, so we have alpha x, and okay, so that seems the simplest. Note that the normal distribution function requires tangent and bitangent directions in addition to the normal direction, since the directions are already needed for normal mapping. Providing them is not an issue, yes. The resulting implementation can look like this. So AT, yes, I just do not have this value. This is a parameter I just don't have, I don't think. And I think that immediately stifles us up with getting this to work. Because I do have tangents and bitangents, but I don't have the parameter of anisotropy. Okay, so in addition, Hertz presents an anisotropy masking function to match the height correlated GDX distribution. The masking shadow term is greatly simplified by using the visibility function instead. Okay, so that's the visibility function. We've seen this before. It simplifies down. You can use trig identity to get rid of the tangent, and then we have cosine. I don't know what that is relative to everything else. So okay, so that seems good. Hello, Botred Gaming. Good to see you, my man. Okay, so the alpha hat, lambda hat is this one of, okay, so that is a bunch of stuff. So AT, AB, so we just have a bunch of extra vectors here that we have to work out. But we literally just do not have these. We can create this, but we can't create the other thing. Okay. So it's a scalar between 1 and 0. Okay, fantastic. The anisotropy material encompasses the parameters previously defined for the standard material node, plus an extra parameter described in table 7. Yes, this is the thing we need. No further remapping is required. Note that the negative values will align the anisotropy with bitangent directions instead of tangents. Figure 28 shows the anisotropy parameters affect the appearance of rough metal surfaces. Okay, so quick question: does GLTF have this in even? So is this a thing I have to pull out? So this is only useful when this material is used, which is fine. So we have the roughness and then the texture. So we have a texture maybe. Okay, so like I said, I don't want to be a busy idiot, so I've got to be careful here. Implementing this might be a waste of time. Or pulling it out. It's only a scalar factor, so it's going to be quite easy to pull out, but if I add this in and it doesn't exist, then I've just kind of bloated my shader, I guess, for no reason. It depends if an artist that I want to work with in the future, or me, I guess, if I end up making my own art, wants to deal with this material. Okay, so for now, what we're going to do is we're going to leave this alone. I think it's good to know and say this is a good reference. Okay, so the next thing I want to kind of blast through is clear coat, and we're just not going to write any notes about it. Because I think we've done literally everything that we need here. And then we're going to take this bit seriously. This bit is still important. This is dealing with conductors and dielectrics with reflectance parameters. which we don't have, but I think this is more fundamental because it's still part of the standard BRDF, as far as I'm aware. There is no separateness when it comes to this. So let's go through. I'm going to skip. Did you ever work with Raylib or OpenGL? I've worked with OpenGL, but not Raylib. I was doing stuff before Raylib existed with OpenGL. And then I think Raylib was still very new and no one knew about it when I was like moving to Vulkan. Is it in the physical device properties? I think for Vulkan, no, that would be. Oh, maybe actually. Maybe there's an anisotropy feature actually. I actually don't know. What I was looking through there was a is the actual GLTF extension. All right, so clear coat model. Let's go through this. The standard model described previously is a good fit for isotropic surfaces of a single layer. Multiple layer materials are unfortunately fairly common. Again, this is nice. It's just do we need it? That's the question. Okay, so particular materials with thin translucent layer over a standard layer. Real world examples such as car paints, soda cans, lacquered wood, and acrylic. Yeah, so pretty sure anisotropic filtering, which is not related. Yeah. I was thinking I think you're right there. Yeah, I was a bit confused for a minute. Are you using GPU mesh skinning on your engine? Not yet, but that will be happening. I think that's the only way to do skinning, right? Oh no, you can do CPU, but that's slow. So no, I'll be using GPU 100%. It's not as I think if you could do proper skinning on the CPU, then as far as I'm aware, moving it to a shader and then just running it there is not as difficult. I think the hard part is getting the maths correct. Anyway, so comparison to a blue metallic surface. I could be wrong there. I don't know. Because I've never actually tried to do the CPU side. Comparison of the blue metallic surface under the standard model left and the clear coat model right. Okay, so a clear coat layer can be simulated as an extension of the standard model, standard material model by adding a second specular lobe, which implies evaluating a second specular to BRDF. Yeah, okay, so yes, this is going to slow things down if we do this. To simplify the implementation and parameters, the clear coat layer will always be an isotropic and dielectric. The base layer can be anything allowed. Base layer can be anything allowed by the standard model, dielectrics or conductors. Okay, so since incoming light will traverse the clear coat, we must also take the loss of energy into account. As in figure 24, our model, however, does not simulate an inter-reflection and reflection behavior. Okay, so that makes sense. And we're only doing this for, what is it? Isotropic dielectrics, which would be so it looks like we don't do diffuse light, we only work out the specular light. So yeah, it's just a second specular lobe, so that makes sense that these blue arrows for those who are watching are specular, and these green are diffuse, and we have a second layer that only does specular, but we also have specular for the base, which is just for any type of light. Okay. So the clear coat specular BRDF, the clear coat layer will be modeled using the same Cook Torrance microfacet BRDF, which used in the standard model, since the clear coat layer is always isotropic and dielectric with low roughness values. C 9.3 3.0, whatever. We can choose a cheaper BFG term without notable sacrifice, without notable visual quality sacrifice. A survey of terms listed in Croatia and Burley shows that the Fresnel and the normal distribution function we already use in the standard model are not computationally more expensive than other terms. Clemen described a much simpler term that can replace the Smith GDX visibility, which is just 1/4 light dot half vector. Okay, so the masking shadow function is not physically based as a result as shown in Hertz 14, but its simplification makes it desirable for real-time rendering. Okay, so in summary, our clear coat BRDF cooked torrents specular microfacet model with the GDX normal distribution function, that visibility function, and the slick Fresnel function listed shown in 13, which we've already worked out how trivial the GLSL implementation is. So it's just okay, so that's the okay, so implementation of the visibility term in the GLSL shader. Okay, so note on Fresnel term. Fantastic. Okay. The Fresnel term of the specular BRDF F0. The specular reflectance at a normal instance of angle. This parameter can be computed from an index of refraction. Okay, so this is something that I think we did earlier. Of an interface, we will assume that our clear coat layer is made up of polyurethane, a common compound found in coating varnishes or similar. An air polyurethane interface has an IR instance of reflection of 1.5, from which we can deduce that F0 is 1.5. Then the okay, so this actually really helps us out. So if the instance of reflection is that, then the actual reflectance value is 0.4. This corresponds to the Fresnel reflectance of 0.4. Yep, that we know is associated with common dielectrics materials. We kind of just set this up as 0.4 anyway, so it's actually not that important. The integration in the surface response, because we must take into account the loss of energy caused by the additional by the addition of clear coat layer, we can reformulate the BRDF from equation 1. Alright, so it looks like they take alright, so I don't know what that would be versus the other ones. I'm just going to say assume it's simpler. I don't know what FC is. Okay, where FC is the Fresnel term of the clear coat. Okay, so that's the 0.4, 0.04 even of the clear. Okay, so the clear coat BRDF. Oh, I see. Okay, so this is the diffuse component. This is the reflectance component. Right, and this is the clear coat. So plus all we have to do is add the clear coat in. Okay, so clear coat parameterization. The clear coat material model encompasses all of the parameters previously defined by the standard model for the material mode, plus 2 parameters. Again, this is why we're not implementing it, I think, is because we literally just do not have these parameters, so we can't actually work this out anyway. So this would be kind of, it's just good to know this stuff at a loose level, so I can come back and implement clear coat if I need it. Anyway, clear coat, strength of the clear coat layer, scale F between 1 and 0, clear coat roughness, perceived roughness, and or smoothness of the clear coat layer, scale up between 1 and 0. I think what I'll be interested in is implementing, if I had to do this for the BRDF, the anisotropic would be first, then clear coat, then cloth. I don't think cloth is going to be useful for a very long time, honestly. Okay, so shows the clear coat parameters. Yep, sounds good. So there's the two parameters, and the BRDF clear coat is worked out like this. And we just have a different standard model, and then recompute the so remap linearization of the clear coat roughness, and then clear coat BRDF. Okay, so yes, we do have a completely different BRDF regardless of how simple it is to do. Okay, so base layer modifications. The presentation of clear coat layer means that we should compute F0, which is what this is, since it is normally based on the air material interface. The base layer therefore requires F0 to be computed based on the clear coat material interface instead. Fantastic. Okay. This can be achieved by computing the material's index of reflection from F0, which is, again, just what that is there. Then computing a new F0 based on the newly computed instance of reflection and the instance of reflection of the clear coat. Okay, so this is like, we have both. First we compute the base layer instance of reflection, which is just that. Okay. Then we compute the new F0 from the new index of refraction. Fantastic. Since the clear coat's instance of reflection is fixed, we can combine both to simplify. Okay. Fantastic. So we don't have to do any like weirdness here. Okay, we can also modify the base layer apparent roughness on the instance of reflection of the clear coat layer, but is something we have opted out for now. Fantastic. Okay, so we've done anisotropic, which was the most interesting thing for me. We're skipping cloth, and we're not taking notes on either of these for now because I don't think it's necessary yet. If I was going to do this in anger, then we would have to write notes and be very, very specific. The only thing I care about now is the reflectance and making sure that this kind of works. I don't think we need to go too in depth, so I'm going to take light notes. But I do need to understand, like, eventually I would like to be able to do this type of effect with dielectrics, with low roughness. Eventually, right? Which means that we need some kind of like reflectance understanding. And we do have that in our current implementation, just so people are wondering, in our BRDF. So we have a standard model BRDF, and I don't think it's particularly bad this time. So we have our FGX, sorry, our FGD even, and we have just like a very common reflectance factor of 0.04, and that helps us work out the Fresnel term. And if I run this just for people's sake, who are obviously people who have been here for a long time in the stream, no notes, yeah, Megamind PNG. Oh, I must have turned off the specular. Okay, so I was messing around with specular last night. Just excuse me one moment. Let me just add that back in. RGB times by 0.01 I think is appropriate for our case for now. Yeah, no notes, but I was taking into account what people were saying about what is it called? Like what I should be studying, what I should and shouldn't be studying. To avoid being a busy idiot, I was like, right, let's go a bit faster rather than studying everything that we need to. Now, the direction is wrong of the lighting, and we can just increase the intensity if we need a directional light that's more intense. But I think generally we have pretty much everything that we'd want. I think this is emissive, like extremely mildly emissive. But we'll have to check on other rocks that are oriented a different direction. Oh, I see. They're always lit up the same direction. Okay, so actually no. They're always lit on one side, and then I've rotated them arbitrarily, which is incorrect. I said I would just study today, but I'm kind of curious if I could get this to work without any effort at all. So, if I take in a vector, let me just redo something real quick in my code. I don't think it's going to be too difficult. So if I go to my light code, which I'm updating every frame, if I decide to set this to 1.f, I think it's just 1.2.3, so I'm just going to do that real quick. And then I just kind of grab that. Instead of setting it in the fragment shader over and over again, we have the light here. And I'm not entirely sure how the geometry is going to work. So if this doesn't work, that means I need to understand lighting better, which I do anyway, but I'm not going to spend too long on this if I can't get it to work. So light direction L, it needs to take in the, what is it called? I've set it up as the light of scene data. So it's the, instead of this, I don't know why the music just scared me there. So where is it? Where's the light? Okay. Let's go to my vertex shader so we can just grab out what I need exactly. Yeah. Okay. So that is that's how we use the pointer to our data. And we got light. So yeah, we're not using, oh, if this was 10, oh, whatever. It doesn't, I don't think it matters too much. We can always change it anyway. Okay, so this is a, so let's take the direction to RGB. That should now work. Okay, so are things lit up? Ooh, things lit up in a different direction, or I can't tell, to be honest. Let me just look around a bit and see. It doesn't look right, but what would look right? Because we have more lit down there. And if I look up, we have okay, let's so the directional light minus the position of the cam, no, that would be the point light. Let's just do it anyway. Instead of using that, I'm gonna try this out. Yeah, excuse me for a minute. If this doesn't work, then we're just gonna move on. This is the last thing we're gonna try. Promise. Yeah, okay, so let's see. Okay, well, I think it's based on my camera position, which worries me. what I'm gonna... No, I don't think it's worked. If I just bring up the intensity by like an order of magnitude, like, let's just make it 500 instead of 100. And I think then it's going to be really obvious. Because it's just going to be like blinding light. No, I think it's all like weird. Yeah, because we've got like dark on this side and light on that side. Okay, that makes sense. Okay. What am I trying to do? Deal with this rotation issue for a directional light where we have this face lit up here, and you know it's not accounting for the rotation. So if you can see the difference here, like that rock. Oops. This. If we had one direction for all objects, this would be lit and this would be lit, but it's like dark and lit. You know. So the directional light is... I just need a little bit more understanding of how the geometry works, and now I think I'll be good. So, yeah. Because the directional light is per model, and the model is not counted for the rotation of the model. This would work if there's no rotation. I think it's really... just to demonstrate this a little easier for everyone. Well, you modified L so it's no longer a directional light. A directional light is not per model. What I'm trying to do is account for the rotation though, of the model itself. So if I just turn, where's the rotation of the things? So what I want to do is get rid of this angle. So 0.f. I think I can just do that. And I think that's just going to work because it's just 0. Nope. Okay, let me just also get rid of the axis. 0.f, 0.f, 0.f. Okay, so do that real quick. Wait, oh, the rotation's happening in here, sorry. My bad. This needs to be a quaternion. So S, identity. There we go. Okay, so that should fix it. Yeah, because these are physical objects. Yeah, okay. You see how everything's lit the correct way? And if I go behind all the rocks, yeah, they're all like, it's all like we have a light source that's coming in from one direction for all these rocks. Yeah, you can really see the speculant. It's because the intensity is really high, by the way. So yeah, when I rotate the rock, it's like the light of the direction. I don't know. I'm trying to get to the end here, but where is everything dark? So yeah, if we move out. I'm not convinced this is even what I'm talking about, which is weird. Because if I travel in one direction, the light's different. Okay, I think it's based. Hang on. Let me fix the directional light again. So we don't have a directional light. We have something else. Let's throw this in here and do this. And then bring back L, small l. So I am learning at the same time, even despite okay. Oh, okay, that's more what I wanted. Yeah, so it's all lit this way and it's not lit this way. Right. The intensity is way too high, so it looks kind of bad, but if there's a light source, a harsh light source, like where that sun is, I guess, then you would expect everything to be lit like that. But when I add the rotation back in, everything just rotates arbitrarily. So this direction doesn't account for that. Right? Okay, so... Oh, my laptop's about to die. When you rotate something, it will get a different direction. Sorry, when you rotate something, it will get a different direction. Duh. Yes. But I need to like offset that rotation back to normal. So what it seems like is like the rotation of the light source needs to be different per model. Sorry, the light direction needs to be different per model based on the rotation. So it lights it up. Well, if we have a directional light coming in at 0, 1, 1, right? And then I have a rotated model. What? Huh? Right. Okay. Okay. Right. Ratchet, I'm just gonna move on. Not because you're probably right. I'm just gonna say that I don't understand enough, and that's why I need to kind of do this. Hopefully that's okay. I don't want to get stuck into debugging shaders like I have done for the past couple of days. I hope that's okay. But what I'm saying is, if I have an object and it rotates, it needs to have the same directional light. That's it. That's all I'm trying to do. So if that's hard to if that's hard to if you're not understanding that, just blame me and say escape point. Just read more lighting stuff, and you'll be able to do this better. It's a skill issue, and I need to get better at it. So let's close that skill gap. Anyway, so the dielectrics. Okay, so the Fresnel. Okay, so how far did we get? Yeah, we didn't actually do any of this. Okay, so let's take some notes. Yeah, lighting direction is constant. It doesn't change with rotation. Cool. So I need something different then than a directional light. Anyway, so dielectrics. What should we call this? Reflectance remapping? Oh no, we already got that. So dielectrics. The Fresnel term applies on F0. The specular reflectance adds. So the Fresnel term of F0, the specular reflections at the normal incidence angle, and achromatic dielectrics. We will use for surface. So what I'm trying to solve, Ratchet, just so I can clarify, final thing. You know, you said when, to quote you, when you rotate something, it will get a different lighting direction. Duh, right? I'm trying to get that so it's always the same direction, regardless of the rotation, right? And you can see that in the models. So if all the light is parallel based on a light source, because it's the direction we're simulating sun here, like that, like this sun over here, then everything's gonna be lit like this. But when the models get rotated, they're arbitrarily lit. So they all have the same orientation, so they're all lit the same, until I add rotation into the objects, and then they're not. Yeah, it's probably some different lighting thing that I need. You'll need a different lighting direction, but sun doesn't light everything in the same way. If you rotate something, it will change. That's what the n.l term does. Yes, let me think about what I'm trying to do. I'm trying to achieve. I don't think this is incorrect. It's just the intensity too high. Let me lower the intensity. Hang on. Back to 100 because that's kind of looking bad if I do super high intensity. Where all the specular, we get like super high specular stuff. Assuming that these are all rotated, this is the effect I'm trying to go for. Where we're flying around, you face this way, it's all clear. And assuming, like, let's just assume these asteroids are rotated. And on one side it's dark, on one side it's light, because there's one light source coming from one direction. And there's no scattering of, like, other light sources. I want other light sources to light things up. Hello. Monshi. Monshi. Let's try and work out your name for real this time. Yeah, Monshi. I'm gonna call you Monshi. Okay, so that's the effect I want to go for. But when I rotate the asteroids, they're all, you know, lit differently. Like, one side is lit dark, the other side is lit light. You know, it doesn't really make that much sense. I know this looks bad because all the objects are the same the same orientation. My C. My minus C. Sounds. Is that how you want to be called? My C, instead of Monsi. Okay, so that's what I'm going for anyway. Let's just restore the rotation. Hang on, real quick. And if that's like not what directional light is, and that's something else, that's faking global illumination or something like that. I don't know what it's called. I'm just gonna say I need to study more. That's all. Anyway, so let's go on and add back the rotation. Because I'm gonna forget that, and I'm gonna be like, why is that like that? So angle and axis. I'll just rerun this just to check. Okay, and let's just run that. Okay, and yep, sounds good. Cool. Everything's rotated again. Right, let's dig into this. The Fresnel term relies on F0, the specular reflectance at a normal instance angle, and is achromatic for dielectrics. We will use the remapping of dielectric surfaces in this. Okay, so the goal is to map F0 onto a range that can be represented. Represents the Fresnel value of both common dielectrics, which are reflectance of 0.04, and gemstones is 0.08 and 0.16. The mapping function is chosen to yield 0.4 Fresnel reflectance value for the input reflectance of 0.5 or 128 at linear scale, 128 on a linear gray scale. Show these common values and how they relate to the mapping function. Sorry, I read that as like a question. Figure 18 shows how these. Okay, so if the instance of reflection is known, for instance, air, water has an incident reflection of 0.33, the Fresnel reflectance can be calculated as the following. Okay, so let's write that in our shader. I'm kind of curious, like, what that's going to look like. because I have carried over the incidence of reflection for these things. And what I'm going to do is add in a test, so f test, and this is a vec3, I think. Wrong way around. And then we can get to the lighting, I think, after this. So incidence of reflection -1 divided by that, so that gives us f0, which is in our case, where's our f0 calculated? So it's a vec3. Is that the reflectance? I'm kind of confused. What is this for? Instance of refraction. Sorry. So it's reflection. For what surfaces is... The reflectance can be calculated by this. So that gives us a... But for me it's a scalar, and I'm not quite sure how that works out. I see, so this gives us the reflectance parameter. Okay, so based on... I think I know what to do. So as far as I can tell, if I take the instance of reflections value, if it exists, and I say that the... So float reflectance equal to so we have the the IR. Okay, so let's can I copy this out? So as far as I understand, this is the... So I'm going to throw this into my code, so I can just refer to it. Okay, so f0 equals... so we have I factor -1, and then we just do pow that 2 divided by this, which would be the same deal. And just see if I understand this. And throw this into here. Now, unless we get some crazy value, I think that's how you work it out with the IR value. So let's just do this. Let's just do the maths real quick, right? So if I take 5 minus 1 and raise it to the power of the 2, so that gives us... No. Why did it do that? Okay, so I'm going to go in algebra solver because the Windows calculator is terrible for this type of thing. So any algebra solver will do because it's just a simple... Okay, so what I want to take in is... Obviously power's not going to work here, so I'm going to take in... So the standard one for anything is 0.5. So the power of 2 divided by 0.5. Oops, my bad. Okay, so 0.5 then, plus 1 to the power of 2. Okay, so what does that come out to be? 0.11111. Okay, so that's really low. It's actually, no, it's really high. That's really high, actually. And but this value is actually reflectance times 18. Oh, is this for conductors? Okay. Hello, Emmanuel. How you doing, dude? So our material model. Okay, so. No, it's still just this. F0 is still just a vector. So this is not right. This would be for the instance of reflection, maybe? Huh. I'm going to say that... Okay, so if we square the reflectance times it by 0.15, we get F0. But F0 is a vector by its... Oh, hang on, I did that wrong. Let me do that again. It should be 1. Let's see. 0.4. Okay, so that makes sense. Okay, that makes a lot more sense. The problem is, though, when I go into Blender and I open up the rock and I see the instance of reflection, I think it's 0.5, which means it's a lot higher. I'm going to open up the duck, actually, because that should be the most basic model. Because I want to have a model that doesn't have any value set. So, if we import the duck, and we look at the instance of reflection of that guy, I hope it's 1, because that means we can actually work out the instance of reflection of any dielectric, despite the Fresnel-Schlick approximation that Ratchet told me yesterday. Thank you for that. Or 2 days ago, I can't remember. Is really bad for anything that's... did I say export? I meant to say import. Alright, sorry about that. Let's do that again. Builds, assets, model to... where's doc? D. Okay, cool. So if we go to the shading, and we look at this fella. Okay, so the instance of reflection or refraction is 1.5. Okay, so we can actually work out that value, which is really nice, and I think that gives us a little extra customizability when it comes to our model, our standard model. I don't know how much this is worth it. Let's have a look. Expect unexpected value. It's 207. Oh, I left this up here. So. Oh. Can I convert? So it's a mix, of course. So when we have this value, we have 0.04. So we get closer to this. So it looks like most of the values are, with the exception of gold and some others, other conductors. Yeah, so of F, what's reflectance again? So this is a... So diffuse, no. So reflectance, but when we work out the, if the incidence of reflection is known for incidence, air, water, whatever, the Fresnel reflectance can be calculated as the following. If the reflectance value is known, we can compute the corresponding. Okay, so incidence of reflection value is not the same as so this gets passed in as a function parameter. So as far as I can tell, the okay, so the Fresnel term relies on F0, the specular reflectance at a normal incidence angle, the achromatic and is an achromatic dielectric. We must use the remapping for dielectric surface described in so this would be a float, but if we work out if the reflectance value is no, so this we can work out the Fresnel reflectance as the following. Okay, let me think about this. So what I'm trying to do is figure out how this converts from a what is it called? A model, a float, effectively. Like, how do we get from IAR to a float to a vector that has this in? So yes, we have the reflectance with a linear value. What's the linear value? Okay, so the reflectance of common materials, real-time rendering 4th edition. Table 5 shows F0's values for a few metals, given in sRGB. Must be used as the base color of the material. The values given in sRGB must be used in the base color of the material model. Please refer to the Annex 9.7 for explanation of how sRGBs are computed from measured data. Okay, so all materials in the Fresnel reflectance of 100% at glazing angles. So the F90 is set in the following is probably set to 1. Yeah, we evaluate it. Okay, yeah, so it's set to 1. So it's just these things here. We have perfect reflections on the edge. So figure 19 shows a plastic ball. If we look closely at the edge, we'll be able to see it. We'll be able to notice the achromatic specular reflection is at the grazing angles. Yes. So that's for conductors, but I think this is the final step. Now I could just replace my we need a reflections vector, if that makes sense. I mean, at the very least, I can just do this. This is not super difficult. This will take us like slightly better than we were before, but not completely. Effect 3. So that will fix everything. As far as I can tell. Obviously, we won't see anything really, because we don't have any material with high reflectance, but I don't think that's damaged anything. Meaning that if I duplicate this, oops, and put in 0.4 for what we had earlier, 0.04, we shouldn't see we should see no change at all. So as far as I can tell, this is like identical. Well, I'm going to assume it's basically the same, but this is because the incidence of reflection calculation is basically 0.4 for 1.5. And in Blender, if I take this duck and I do something crazy like whack up this guy, I don't know what that's going to do, or lower it like crazy to 1. Yeah, so I think because the roughness is so high, but if I turn up the metallic to like and turn down the roughness, yeah, you can see what ends up happening. You get like a metal duck. And if I turn down this guy, yeah, you see we get less pure reflection, I guess. It would be nice to put a metal duck in. It's kind of interesting. So low roughness and high, and obviously that's pure. If I turn off the metallic all the way, we get like a pure reflection. But that would be a conductor anyway, so that would change everything. So for now, I think we're good. I think we're good with that. I don't see any issue. It's not perfect though, because as you can see, the actual thing is worked out like this, and it's not quite correct. Okay, so moving on, the conductors, the specular reflectance of metal surfaces is chromatic. So base times by metallic. So how you compute F0 is, but for both dielectrics and metallic materials, is show that the specular reflectance is derived from the base color of the metallic in the metallic case. So we could just replace what we've done with instead of using the mix, but effectively we've done that. We've done this. So if we add this in, it will be identical. Anyway. I am tempted to make a purely metal duck and just see like how that behaves. Obviously this is simulating perfect reflections. But if I like I don't know, kind of like this. If I have a look at that and obviously turn this back to 1.5 because that's just normal. What would that look like relative to our stuff? Let's probably turn on the roughness a bit. So yeah, I'm gonna make a, just for experimental reasons, because I don't really have anything metal in the scene. I'm gonna export this duck with these materials. Quack, indeed. Let's see what a metal duck looks like, hey guys. So, out. So just metal duct, I think. Yeah. We need the... Now, this is a well-behaved model, so we just need to make sure that we have tangents, because it already has tangents. And we should have metal duct in where we need it. And I'm just kind of... Because I need to see more of a conductor than just straight dielectrics. To see how my reflectance calculation has worked out. And how... Because I don't have image-based lighting or anything like that, by the way, we're not going to get like any surfaces appear, like a reflectance of the nebula reflected on the duct. But I at least want to see a different look to the lighting when it comes to our BRDF. So I'm just going to go in here just to make sure it's here. And okay, so we have metal duct, and hopefully I'm just going to replace for now all my ducts with metal ducts, just to reduce the complexity of trying to add a metal duct separately from the regular ducts. So whoops. So hopefully this doesn't like go crazy and, you know, tell me that I need to do 20 different things to get this to work. What I just want to see is with a conductor. Okay. It's not perfect, but it's not terrible. Let's have a look at this guy, the lighting. Okay, remember we don't have the what is it called? We don't have the skybox that reflected back on this, so we're losing a lot of like convincing metalness, but I think that's not bad. That's not bad. If you look at the beak, it's got the what is it called? It's got all this like added on from here, so it is behaving decently. I think I definitely could improve this. Don't get me wrong. It feels very rough still, but I think we need image-based lighting really to work this out properly. Yeah. I don't understand why the dark side is very dark. Okay, so that's because I have a light source coming in directly from this direction. So if you can imagine a light source like here, I'm just going to go 90 degrees here. So the light source is like parallel to the duct, like here where my mouse is, and it's going like this. And so what I've done here is just make it so the dark side of the duct, where there's no other light in the scene, because there's no other lighting at all in the scene, has some basic lighting. So it's not complete black, which is what this would be without this. So yeah, it actually looks better further away now. Look at it. Yeah, that's like, that looks metally. So that's why like if I turn off this for the, you know, for the rocks as well. This is something that's just incorrect about my scene in general, because I've rotated the rocks. The direction at which they're lit is wrong. They should be all lit from the same direction. I want like a global direction light, not just like a local direction light, which is like tied to the model itself. Now Ratchet might come back and say, but that's what you've coded. The thing is, I've rotated the models, and they still have the same vector that says light them up this way, so it doesn't matter if I say that the constant value of being lit is this. Sorry, is like 110 or something for the vector direction. If I've rotated the object, then it's still lit locally to the same direction, if that makes sense. So hopefully I've explained stuff. Yeah, keep asking questions if you don't understand stuff, by the way. But hopefully that makes sense, Mabdo, why this is lit from one side and why it's so dark over here. It's because we have a pure direction light that's just lit in one direction. If I had a point light, then this would make more sense. But I want to light the whole scene, right? That's the whole point of having a direction light at the moment, is so I can light everything. But yeah, I'm pretty happy with that. And I am pretty happy with the fact that this looks like metal. And if you go back to the, assuming that we don't have any, so the lighting model, in Blender we don't have a direction light. We just have I assume ray traced. It looks like. Well, anyway, the way this is lit, it's lit from all directions, and it's using a skybox. Sorry, it's using a. What is it called? It's using a radiance map, which is why this is all blurry. So it's using this radiance light map in the background, which isn't quite a skybox, but it's very close to a skybox, and it's doing the reflections on it. So I think we're okay for the most part. Based on our lighting, is very different. But the lit is not same direction as the rocks. But the light is not the same direction to the rocks as I see. Yeah, that's the thing I've got wrong at the moment. Andrea. I need to fix that. That is something I need to work on. But right now it's just making sure that the conductors, which are just metal surfaces basically, are behaving relatively, I'm not going to say perfectly, but relatively normal. That's mostly what I was concerned with. If I, relatively normal. And yes, with the direction light, then, this should be lit if this is lit. So, anyway, let's continue. Yeah, thanks for bearing with me, guys, on the explanation. So, I'm probably just going to blast through this because I really want to get to the lighting, because this is part of the problem at the moment. I don't understand the geometry of lights. Okay, so roughness, remapping, and clamping. The roughness set by the user is called a perceptual roughness here, and is mapped to perceptual linear range using the following formulation. Yeah, perpetual roughness is just, yeah, it's just alpha. I also call it that as well. Figure 20 shows how silver metallic surfaces with increased roughness using this unmodified roughness value at the bottom are remapped. So the roughness comparison linear at the top and roughness at the bottom. Interesting. So it's not pure reflection. Huh. I wonder if it almost feels like this and this are closer than this and this, which is interesting. So the roughness comparison, it's linear top. Oh yeah, okay, so that's actually what we want, the top one. Makes sense. Using this visual comparison, it is obvious that the remapping roughness is easier to understand by artists and developers. Without this remapping, shiny surfaces would have to be confined to a very small range of, okay, 0.1, yeah, okay, to 0.05. Brent Bertley made similar observations in his presentation. After experimenting with other resampling, cubic and quadratic mappings, for instance, we reached the conclusion that the simple square remapping, so cubic I guess, visually delivers visually pleasing and is intuitive results, while this while being cheap for real-time applications. Right. Oh, I didn't read something in Mad Day said. So, how is that? Do you have baked lighting in the rocks? Nope. I haven't rotated the ducks, and I've rotated the rocks. That's why they're rotated like that, sadly. Not very good. Not very good at all. Okay. So let me just check something real quick. Sorry about this, guys. Okay, so the cause, this causes problems when computing small values like 1 over perception roughness to the power of 4 in our lighting equation. Roughness squared in GDX computation. The smallest value can be, okay, so we don't have to worry about this. Represented as a half float is 2 to the power of minus 14. Okay. Yeah, we're using full floats because we don't care about that level of performance when it comes to our rendering. Okay, so denormals can also be avoided to prevent performance drops. Good night. I came to say hi and go to sleep. Good night. Good night, Mika. Have a good night's sleep. And I'll maybe see you in the morning at your time. Yeah, thanks for reaching out and saying hi. Roughness close to 0, almost creates almost visible. The roughness can also not be set to 0 to avoid the obvious division by 0. Yeah, that's a good point. Let's look at my GDX real quick, and I'm just going to look at this and dive into so our visibility doesn't seem too bad actually. Alright, yeah, I think it's fine. Yes, so I'm sending that in there correctly. Okay. Fantastic. Okay, let's continue. Like I said, I just want to get through this pretty much as fast as I can. Since we also want specular highlights to have minimum size, a roughness of close to 0 creates almost invisible highlights. We should clamp the roughness to a safe range in the shader. This clamping has the added benefit of correcting specular aliasing that can appear for low roughness values. Okay, so let's try something real quick. I want to go into Blender again and just take my duck and just turn down the roughness to 0 and just see how my engine handles this. Do we have a division by 0? What ends up happening? I kind of don't like perfectly reflective conductive surfaces like this, but this is just kind of a test, right? So pure reflect. Okay, yep. Let me export, and also I need the data as well. I assume it's still got tangent data in it, so yeah, I'm just going to take that out, copy, export, let that finish, go into scene, and change this metal duck to a pure metal duck. And I'm just going to say pure reflect duck, even. And let's just see how our shader behaves when we do this. Oops. Yeah, so I think we might have an issue. We might have a division by 0 on the GPU. Now I am kind of curious real quick. I'm just going to check my other shader that I've got. I wonder if it handles this case properly, and then we can try and take that code away and improve our lighting again. So if I go into, what is it called? Sorry, yeah, it's at the top, and just change my shader from new to old. Just do the old one. Just see how that handles it. So this is going to use a point light, I think. Okay, so yeah, it doesn't handle that, which is fine. We can very much fix that very quickly. So that's a very easy fix. I can actually steal that from here. And throw that in there like that. And then get rid of this. Yep, okay. No, okay, so my engine, my older shader, doesn't handle this even a bit, correct? Interestingly, this is lit very differently. Okay, so that's... Oh, hang on. It's because I have a... Can I just change something real quick? Okay, so that's not right. I know I said I wouldn't be coding as much, but this is... I am learning as I go. I'm trying to go with a more practical approach rather than just taking notes for this particular case. Okay, so scene... No. Game. Control Z, Control Z. No. We need to go to our lighting code and change this, because we're doing a point light in that shader, so not a directional light. Where is it? Yeah, so I'm just going to take this back out. And that should fix the lighting issue. No, okay, interesting. So that is lighting up that, but the directions are all wrong. Which is kind of what we're trying to fix as well. And it looks like a perfectly reflective duck. We've not handled metals properly in the old shader. Okay, the reason I wanted to check that was just to make sure that what I'm doing is an actual upgrade. I haven't actually downgraded, so at the very least, we know that perfect roughness is wrong, so let's try and fix that in our new shader, which is the one that's being corrected over time. The problem is I think we're getting the division by 0, and then we're getting some weird values. So that's if roughness is 0. And so so if roughness is 0, alpha is 0. Let's see. Sorry, I need to actually get my new shader in. So if I go to scene, no, game. There we go. And so what we're trying to fix here is, let me just restore what I was doing. I think it's up here actually. Nope. Yeah, okay, so this needs to be new. So it picks up the new shader, which is the one we're messing with. Okay, so super high metallic surfaces. Hang on. This could be correct. Let me just hear me out. When we do a reflection with a directional light and it has no roughness, we get pure specular light, right? But I think because we're not doing image-based lighting at all, and we don't have anything like this happening, the light that we get from... the light that we should get from here, if we got rid of the... what is it? The irradiance map, which is in the background of this, we would end up, I think, with basically the same result. With the only difference here that we're getting some diffuse color that's treated as specular reflectance for pure metals. And yeah, because we literally just do not have image-based lighting, I think it fails. And we end up with this zero roughness. Okay, so there's only one way to check that. And that's just to make roughness basically not zero by a bit, right? So that's indistinguishable from zero. And I'm just going to make another, just challenge my assumption there, because it's good to challenge my assumption. So almost, so that's my assumption. My assumption is, because we don't have something like image-based lighting yet, the pure conductors that have like no roughness at all and a pure metal aren't handled correctly, because there's no lighting information to them for them to pick up. That's what I'm thinking, right? Now, if this is basically the same, then I think my assumption is correct. If it's really shiny, then we're dividing by zero in the zero case, and then we need to fix that. So there's two outcomes here. Really shiny, we've got nothing to do. And really shiny, we've got to worry about the division by zero. And if it's basically just dark still, then we can leave it alone for now, because we don't have that lighting information to light up the model correctly. Hopefully that makes sense. That's what we're doing. So I just need to load that model in my scene. So yeah, we just need to watch out for both. So almost pure reflection. So okay, I can put the almost in the wrong place, but whatever. Pure almost reflection. Yeah, okay, so that makes sense. So I'm happy with that. The diffuse reflection that we're getting is extremely small. That is fine. It's basically, I see. So as you can see, it's if I turned off the ambient lighting that we've got, it would just be black with it, like one speck. Because we're not handling, we don't have that lighting information to be able to light up this type of model with this type of surface yet. Okay, cool. We're doing the right thing. We don't have a division by zero, as far as I can tell. So let's bring back our regular duck, so you can see like a pure roughness equivalent, and yeah, so this is pure roughness on one side, and you can see it's extremely well lit. And then a metal duck with a bit of roughness. It's losing some data, but it still has that kind of metalness look to it from a distance almost. We just don't have any reflected surface. So if I look from here, it's kind of like, it kind of looks like kind of, not quite, but kind of looks like a polished, no. What would it be, like Rough metal, unpolished metal. Yeah, unpolished. It looks unpolished, right? It just looks kind of unpolished, like unpolished metal, where it has no shine on it, but we're not simulating any of the shine. So yeah, that's why, and that's also why this down here is black. These dots. But anyway, I've talked about that enough. Okay, cool. Figured stuff out. Very nice. Let's change the music because that's stopped. Let's go to, you know, if I play that, I'll get instantly copyright strike from high heavens. Let's play the classic. Good old Skyrim. Old faithful when it comes to good background music. Once it actually plays. Yeah, okay, so it's playing. Right, fantastic. Let's continue. Just make sure it's not too loud for you guys, actually. How's that? Let me know if that's too loud. I don't think that's too loud. You can sit there and enjoy your listening experience. Okay, so we need to just finish off this real quick, and then we can move on. Okay, so blending layers. Okay, so noted in Burleys and new bullets, new belt. This model allows for roughness blending between different materials by simple interpolation. The different parameters in particular. Right, interpolating the different parameters. In particular, this allows. Let me just get a drink. This allows to different materials using simple masks. For instance, in Figure 21, it shows how Ready at Dawn used materials blending and layering in order 1886 to create complex material appearances from a library of simple materials: copper, gold, wood, and rust. Right, yeah, makes sense. We have this already, we don't have to worry. The blending. The blending of layered materials is effective in interpolation of various parameters of material. Show a interpolation between shiny and metal, chrome, and red plastic, while intermediate blended materials like make physical sense. They look okay. Yes, they look plausible. Yes, might make sense. Okay, so crafting physically based materials. Designing a physically based material is fairly easy once you understand the nature of the four main parameters: base color, metallic, roughness, and reflectance. Reflectance. Let's have a look. Where's the reflectance? Oh yeah, so it's just a value. Non-real world material. Yep. Okay, so common. And then all dielectrics, and then gemstones, yes. So, yeah, we worked that out. Interesting. I see, so they have a... so we work it out kind of differently. Anyway, it's not too important. Yeah, I guess it's good to know this because if I ever actually do this, then it'll be kind of useful to fix. Anyway, okay. In addition, here's a quick summary of how to use materials. Base color should be devoid of lighting information except for micro-occlusion. Metallic is almost a binary value. Pure conductors have a metallic value of 1, and pure dielectrics have a metallic value of 0. You should try to use these values close to values close at or close to 0 and 1. Intermediate values are meant for transitions between surfaces. Sounds good. Okay, so non-metallic surfaces base color represents the reflectance color. Should be sRGB in the range from 52 to 240. Alright, yeah, so cool. Metallic should be 0 or close to 0. Reflectance should be set to... Yeah, we don't have... I've done instance of reflection here, but we don't have reflectance values. That makes sense. Okay, so... I was wondering what was going on. So if I look at my model again, do we have a reflectance vector or something? So we have emissive. We have sheen, which we don't use. We have coat, which we could use. Transition, specular. Yeah, so that's fine. No, we don't really have it, I don't think. So it's saying that this, when we're doing BRDF, yeah, I just don't think we have that material fully available to us. Let's see. No, I don't know. I don't know, honestly. It's yeah, we don't have a reflectance thing in here at all. I don't know how you would get out a grayscaled 256 vector and then work that out by multiplying by 0.16 and then squaring that thing. The problem is I just don't know where that would live in this. But anyway, it's fine. We've got an approximation for dielectrics, and for metals maybe it needs a little bit more work. Anyway, let's just blast through this. So yeah, it's just a vector, but I don't know where it lives, this parameter. Let's Google a reflectance. It might be an extension exclusive, which means we can't do it. Well, we can, but GLTF in our GLTF model. Yeah, so what I'm looking for is this right? Okay, so we've got two here. Let's look at these two. So that's the specular stuff that we talked about 2 streams ago. And yeah, we don't really have reflectance here, I don't think. Yeah, okay. It doesn't exist. I think for our case, this specular reflectance thing is probably this. But I don't know what the values go up to. It could be way higher. No, default is 111. So, F... Okay, so I think this is it. The strength of the specular reflection and the F0 the specular refraction. So let's pull this out. I think I can get this out if it exists. Okay, so last thing. This is the last thing before we move on to light geometry. I promise. But what I'm going to do is go into my GLTF loading and also just kind of expand this a little bit with another vector. So I hope this just can go here. So specular value, I don't know. And what I'm going to do is multiply this by 16 squared, and that'll give us the F0 that we actually care about, rather than the one we calculated earlier on. Anyway, right, let's do this. So now we need a material one. No. We need to go into the game and upload this data. So here. So have we done it here? Yes. So we need it in this as well. And this is... This can go here. It doesn't really matter. But... no, let's do it like this. I'm respecting the 16 offset, even though I've got scalar, but I kind of want to have a... I kind of want to respect it, so duplicates, so we have a specular values. Okay, so that's uploaded. Now we need to do it in the shader, wherever this is used, which is... I think it's used in 3 places. No, it's further up than that, sorry. So... Yeah, this is a vec3 specular value. I think that's what it is. And let's just look for material constant uniform. And then we can modify them in the places that we need them. So I might get rid of this shortly. Okay, so now with this value we have the... You can actually just pull this out. This goes straight in here like that. So let's see how that goes. The problem is if this is null. So what I'm going to check is... Do these have values? Oh, I haven't loaded them in. That would not work. So, let's see. So what I'm going to do is set it to 1. No, what does it need to be? This is wrong. I just realized I made a mistake. So this would be this needs to be F0. So F0. No, this would be this would be true reflectance. So not F0. This would be D. This would be, I'm going to say 1 for now, because I think this is better. If we take this, would be a vec3. Specular value. So power, I think we can power this to 2. And then times this by 0.16, right? That, I think, is the true reflectance value that we pass in. We don't pass in the pure specular value. Because that would be too big. That'd be massive, that would be massively overpowered. Alright, so that's, I think that's correct. I'll get rid of reflectance not 1 if this works. Second thing I need to do is what I was doing just then. So if the material has specular, has specular, then we get the specular out. Obviously this is IAR, but specular value, and then we get this out and go, okay, specular which I believe is the thing we care about. And we need to get out just not the texture, but not the factor either. Which one is it? One of these is the one I care about. Because we're not getting everything yet. Specular color. I think, yes. So that's kind of awkward. That's fine. Dot y dot z, and then we just do 0, 1, 2, 3. 1, 2. Okay, so then if this has nothing in it, then we set this to default 1 F, 1 F, 1 F. I believe that's according to the documentation I just skimmed through. Specular color, no default. No default. So okay, so this is required, and the default is 111. And if I look at this guy, the specular is what? Is that what is it the same thing? We'll have a look anyway. So if it is used, I don't know what 111 is going to look like. It might be too reflective, you see. So let's do the maths. So if I take, let's just do a component, and yeah, 1 squared is 1. So that would be 0 dot, yeah, so that'd be 0 dot 16. Okay, that, I don't know what that would look like. I think it's okay. Alright, let's just let it rip. Okay, so we can't use that power like that. Fair enough. I don't think it's too complicated to get this to work. So this is just copy times by this. Doesn't really matter, but we'll do it like that. So just times by itself. Okay. And so let's just check it even did anything. And if we go into here, does this have any, does this ever get set? Yes, okay. What are the values coming out of here? Interesting. 1. It's always 1, is it? Okay. And so these are all defaulted, sounds like. Okay, so if we look at this code again, so we have the texture, which we're not going to deal with for now. We want the factor. So how's the factor worked out in the filament code? It has 2 parameters according to itself, and where does it talk about the parameters here? Parameters. What I'm looking for is a table. And what we could do is just rewrite the code, I think. So that's effectively what we've done. We've done this reflectance thing. So that's a Fresnel slick. It's also true that we just do not have a metal duct. Hang on, let's bring back the metal duct. So it's possible that this changes based on metallicness. No, that's not right. Where was it? I saw it earlier. The reflectance value parameters. No, I don't want clear coast. It must be further up. Yeah, reflectance. I think it was for clear coat actually. I've got them mixed up. And reflectance is the normal instance of the dielectrics. Okay, so let's throw in a metal duct then and just see the difference. I wonder if the factor... Okay, so if I go into scene and change this to a metal duct and just see like what... Because we have basically matte surfaces. How that behaves. Now we've got some kind of... Okay. I don't really see any difference, to be honest. I mean, it looks fine. It doesn't look bad, so... So the other one is what? Pure... Almost... Oops. No. Almost pure. See the almost pure duck. And we'll see what this looks like, and if this is just the same as before, then yeah, I don't think we have any improvement. But we haven't broke anything. That's the important part. And what I'm going to do as well, just final thing before we move on, is F0. Just kind of, they have calculated things completely different to what I've done. So, because I've got a reflectance thing here, I'm just going to comment this out. I'm just going to see how... Okay, so if I have reflectance 1, I have metalness. And just base color. We should get a... okay, so... Oh, do we have... Oh, yes. Okay, so RGB. Our base color has alpha in it, and I think that's the only issue. Yep. Okay. You just have a look. Yeah, it's basically the same, as far as I can tell. Let's just compare the two. So my original one was... I'm just going to go with the original, Vec 3. So there's no reflectance in here, 0.04. Just see what the difference is. If any at all. So I'm going to take a screenshot and kind of compare them after. Because I think there is a mild difference here. So this is the original. And this is the... Whatever the difference is, it's very small. When I do the reflectance value based on specular and all that. Okay, so let's get a bit closer. Oops. It's pretty much identical. Yeah, it's basically the same. There's no difference. Okay, so I guess if the reflectance is always like that, then it's good to have this, perhaps. I don't know. I'm gonna leave this in. I'm not. It's called reflectance 0 though. Maybe this is just a giant waste of computation, but because I've got to be careful with this, because you've got to remember this is per pixel. Anyway, so F, maybe. Alright, so now we're going to move on to lighting geometry, which is good. Okay, so maybe this isn't any better. Yeah, okay. And I don't think we're using the instance of... Yeah, we're just not using a bunch of material stuff. But anyway, okay. So, we are on this. I don't want to do this. I'll leave this for now. I don't really have any opinion on it. We need to move this back over here. And we need to now move back. Oh, just close the engine. Oh, no. I'll leave that. That's fine. So, sorry. Got everything closed then. We are just going to go, yep. We went over anisotropy. We're not going to do cloth. We are going to start on lighting. And this is our main thing that we're going to be attacking today. 100%. We need to get better at this to light things up better. And this will hopefully fix the weird kind of this stuff. Like not accurately doing conductors where it's kind of too dark here. Everything's just way too dark, so that's why we're here. Okay. Let's give myself a stretch. Check something real quick as well before I stretch. Okay, right. Let's dive into it. I hope you all having enjoy me watching watching me figure out basic lighting techniques. I don't know how basic it is. I don't really have any frame of reference. So I'm just going to quickly go over my notes real quick. So we have some lighting theory down here. Oh, no. So we have light distribution. So we don't need to make these notes twice. So when it comes to ray object intersection, for ray tracing, it gives us a point and the geometry and geometric information. Okay, we need to figure out additional information to how much light is hitting our scene, maybe. This is done with the geometry and radiometric distribution of light. Okay, so meaning that this isn't exclusive to ray tracing. Yeah, fantastic. Okay, so for something like a point light, the geometric distribution of light is simply knowing the position. This isn't found in real life. To match reality, you have to use something. You have to use an area-based lighting. we need to worry about the amount of light, light power being deposited on the differential area surrounding the intersection point. Points, not pointer. P. We'll talk about lights to drill the point lights to drill the basic concepts. This picture gives the general idea. Okay. So I think this is the radius of the light, the point P, the normal, and the displacement of power maybe. We'll assume that the light, excuse me, we'll assume that point light has the power of phi associated with it, and it radiates light equally in all directions. This means that the power per area of a unit sphere surrounding the light is phi divided by 4 pi, which is based on the area of a sphere. Yeah, I think the actual area of a sphere is pi r squared, but that's where we get that from. If we have a sphere that accounts for light, this gets larger further away. This gets larger and further away from the point. We lose power at a rate of 1 divided by 2 r to the power of 2. Okay. This is the inverse square law. So this is why it's very difficult with, I don't know, a floodlight to light an entire area. You need a lot of power to do that. Anyway, if we are interested in working out the power that's distributed on a patch of surface, we tilt the patch by an angle of theta from the vector from the surface of the point light. I think I'm just going to say from the surface, because from the vector from the surface is a bit from the surface of the point light. The distribution of power is proportional to cosine of theta. Putting this all together, we get the differential radiance equation, which is phi cosine and pi r squared. This is for any light source. You have two laws in this equation: the cosine fall off of light for a tilted surface, and the 1 over squared fall off of light with distance. So this just means if you tilt let's just say you have a light directly above you, and you tilt a surface. So if you have a straight light, okay, this is not going to work. I'm going to have to do this myself, I think. So if you have a straight light, and the light source is here. Let's go with a sphere, maybe. Let's go with the yellow. Should have changed this to black, never mind. Nope. Oh, yeah, fill. And then the light hitting this. Whoops, nope. Okay, let's do that again. So if we have a light beam, then the light that bounces off that, let's go with orange. Okay, thank you. orange, please. Yep. And the light that bounces off is going to be intense. It's going to bounce back if it's reflected. And diffuse light is going to scatter out all over the place. But if we have a surface, let's go all the way back and change this to black. So you guys are okay. Because I know that's... there we go. So if we have a white surface, which is like this... I don't know. Like this. I don't know. It's a tiny little... And we have a light source. I don't know and ask, but I'm just gonna do it anyway. Let's like here, then the square. Let's do orange again. The light beam's gonna hit this area. Then the angle is a lot steeper, so versus what it used to be like here, the difference is this angle between the two. That's how it works. So we have like more shaded here, so it's like much darker. I don't know, this would be like super dark, rather than if it was a black surface, rather than basically white if it came from this direction, which would be, I don't know, like anyway. You can see this if you basically hold up something and tilt it towards the light, if that makes more sense. And it is proportional to the power of the cosine of that angle. Anyway, so that should be that. Adding more light, it's just adds, okay, that's quite basic. And the light transport equation, which is just this big guy. So really should change this to vectors. I didn't know this existed at LaTeX at the time when I was writing this out. And so let's just do this. Just copy this over, I think. It's a bit faster. And I'm going to leave that there. I don't think we're going to have to do anything with this. Okay. So based on that, let's not take all the notes in the world. We don't need them. In fact, I think we're done. Let's make a new note. So this is going to be. Let me make something new. Greeting. How is it going? Hi. Yeah. How you doing, dude? Yeah, not bad. We're just going through. We're just about to begin. My understand. We're going to improve our lighting understanding, which is going to be great. So we can make things nicer in our engine. So we've skipped a bunch of stuff that we didn't need to study for materials for our physically based rendering. But yes, we're about to do lighting. Let me show you in a minute if you can bear with me. I will show you my game, and it's like a space game. But to do that, I want to have really nice lighting. So that's the whole point of this. So so let's grab that. So I'm just going to add this in, and then I'll oops. Nope. Thank you. Delete. Okay. Cool. So I have a little space game in my game engine called Void. That's the Void game engine, and we're currently trying to improve the lighting if I turn off the debug geometry. Because I think the best way to sell this game to other people, in the sense like why should you play it over others, will be to improve the lighting. So I've been working on just before the lighting geometry. I'm trying to get metallic surfaces to appear properly with specular highlighting and stuff like that. But we're not quite there yet. We don't have all the materials, all the data to make this real shine. But yeah, you should be able to fly around and do stuff and at the very least explore. I don't really have a super in-depth idea on mechanics, but yeah, we're just going to be flying around in a 3D space game. So yeah, hopefully that explains Ray Nash. Ray Nash. I'll just call you Ray, I think. Like what we're doing. I've just noticed the specular is really high and the diffuse is really low. Interesting. So if I go over here where the diffuse is, I'm just going to look at my lit rocks. So the rocks are lit incorrectly relative to the scene at the moment. Okay, interesting. Yeah, okay. So yeah, anyway, now we're going to make, I'm going to read some stuff in my in this book to be able to light the scene better. So interesting, this is lit differently. It's not lit very, it's kind of low light here. Anyway, yeah, okay. Let's continue. So yeah, thanks for the question, by the way. And yeah, so we need to understand lighting to do lighting, right? Okay, so I'm going to read this out loud. Feel free to keep asking questions, by the way. I don't mind answering anything like you guys may want to know about. So the correctness and coherence of the lighting environment is paramount to achieve plausible visuals. After surveying existing rendering engines, such as Unity and Unreal 4, as well as the traditional real-time rendering literature, it's obvious that coherency is rarely achieved. Unreal Engine, for instance, lets artists specify the brightness of a point light in lumens, a unit of luminous power. The brightness of directional light, however, is expressed using an arbitrary unnamed unit. I don't know if this is true anymore. One moment. Just got to fix something real quick. Whoa, that's not... yes, I'll just be right back. I just had to deal with that. Hopefully that wasn't really loud. Alright, I'm back. Okay, to match the brightness of a point light with lumens of luminous power of 5,000 lumens, the artist must use a directional light of brightness 10. This kind of mismatch makes it difficult for artists to maintain the visual integrity of the scene when adding or modifying lights. I wonder how true that is in Unreal Engine 5. Using solely arbitrary units is a coherent solution, but it makes reusing lighting rigs or a difficult task. Okay, so for instance, an outdoor scene, we'll use a directional light of brightness 10 as the sun. And all other lights will be defined relative to that value. Moving these lights indoors, the environment would make them too bright. Okay, makes sense. Okay, so our goal is therefore to make all lighting correct by default, while giving artists enough freedom to achieve the desired look. We will support a number of lights split into two categories. Direct lighting, punctual lights, photonic lights and area lights, and indirect lighting, image-based lighting for both local and distant light probes. 2. So I think all I need to do here is basically just give myself a quick it's a good idea So I'm going to take notes in Obsidian here. It's a good idea to have lights have coherent. So coherent. Coherent. Where's the? Yeah. Okay. So coherent lighting units that all follow the same system. Yeah, same system's fine. You have two different lighting types. Direct lighting. And indirect lighting. Yeah, I mean, it's kind of basic. I don't really need to say what those types are. Okay, so here we go. Here's we're getting into the meat of it. Units. 5.1. The following section will discuss how to implement various types of lights and propose equations. To make use of different symbols. And those proposed equations make use of different symbols and units in this thing. Okay, so lumens. We have lumens. So candela, lux, nit, watt, lumens per watt, and percentage, which is a V. Right, okay, so that's fine. Let's write this table out. And we'll edit the table as we go through. So insert table. So photonic terms. Photometric even. Notation. And we need an extra thingy. Units. Alright, so I think luminous power is fine. And then we have this as \phi. Which GPU? I have a an NVIDIA RTX 4070. So a decent graphics card, but not crazy good. But I'll try and make this stuff work on lower class GPUs. As best as I can, at least. It's not like I need that level of power to do this type of thing. So, especially with some of the techniques I'm going to use. Amazing. Thank you. Thank you for turning up, by the way, and watching this stream. I hope you're having a great day, but yeah, I hope everyone is having a great day. So luminous intensity is candela, CD, which is just CD. So this is the intensity, which is nice. Or what's SR, which is the thing I don't understand. Or LM, which is lumens divided by surface radius, maybe. Okay, so let's type this out. Frac and oops, \frac. So LM over SR, which I'm going to assume is surface radius. I'll kind of add a note there in a minute. So illumination. Sorry, luminance. So luminous and illuminous. Oh my goodness. Illuminance. Okay, illuminance. If I just take my time to read it properly. Illuminance. And put the N in the right place. we have L, luminance. Oh, E, sorry. Right, okay, so, whoops, come on, work with me here. Lux, which is just lux. So LX. LX, which is either or. So I assume it's meters squared. Which would be the inverse square rule if you wanted to see the distance, I believe. So there's two things I'm going to kind of have to kind of guess here. So when I write my extra notes, frac, meters squared. Fantastic. Okay, so that should be... Oops. I didn't do that right at all. Oh my goodness, come on. There we go. I see what went wrong. I called it frag again. So luminance. So illuminance and luminance are two different words. Might have to add some definitions here. Because yes, I haven't studied lighting very much, and this is why I'm having to do it now. And I'm going to do it all day. So, all for the rest of the day at least. / frac. CD. And I don't think I need to do what I did earlier, so I'm just going to type this out like this. M. That should be good. So we have radiant power. Fantastic. Very easy word to understand. So this is phi, the capital P, underscore E. Very good. So this is watts. I see. This is actually quite easy to. Okay. We all know what a watt is. So, well, I assume most people know. What? Luminous efficiency. Efficiency. No. That's not efficiency. So yeah, I'm gonna have to. Ooh, that's a new That's a new symbol. Nope, that was a mistake. Eta. Okay. Eta, hardly know her. It's such a stupid joke. Let me just type this out. Whoa! Thank you, dude. Thank you for the donation. I love that. Just watching. I appreciate that. So the Great Wave of Vulkan. Wow. Yeah, thank you. That's it. We've got to keep up with that Vulkan stuff. Appreciate that, dude. Hope, yeah, we'll just keep watching, and just like your name, we'll keep on keeping on with our Vulkan stuff. Yeah, we'll we'll try and make the best renderer we possibly can for the most amount of people that can play it. Get it working on both, hopefully Linux and Windows, so lots of people can play. What I want to show off, all in Vulkan, which we all love. Yeah, thanks again, dude. Yeah, appreciate that a lot. I get to tell people now. Look at me, people like what I'm doing. So that's awesome. All right, V, and this is the percentage, right? So we need some when we're working with our lighting, we need to have some definitions. Right, so here we go. Percentage. Alright. Oh, yes, I remember this does not play well. Oh, no, it does. Okay, fine. I tried to do percentage in LaTeX before and it didn't work. Okay, so oops. Let's delete this row. Fantastic. I appreciate your talent. I appreciate you, dude. And honestly, thank you for watching. And I'll try my best to make something that's worth your time and worth everyone's time. So you know, it's great motivation when I get a small little donations like that. So yeah, thank you. Right. Okay. So illuminance and illuminance. I don't know the difference. So let's work out these. What is the difference between these two? So illuminance is measured. So I'm just going to go to Wikipedia rather than use the AI. So in photometry, illuminance is the total number of lumens flux instance on a surface per unit area. I see. Okay, so this so illuminance illuminance. I think I spelled it wrong, haven't I? No, I spelled it right. Okay, illuminance is the total luminous flux so total luminance flux is the incident on a surface. Sorry, luminous flux incident, which is just how light interacts on a surface per unit area. Okay, so that is why we measure this with a... Okay, so grab this thing out. So yeah, just taking notes at the moment so we get better at lighting and make everything look lovely in our game. Just for people who are wondering, what does the game currently look like? Let's show you. Because I know not everyone is familiar with what I'm doing. So I'm trying to make this lighting scene look nice. So we're going to be flying around, you know, doing space stuff in space. And I just want to make the lighting a lot nicer. I'm currently trying to get metals. I've made this metal duck. Sorry, I've made this duck metal, I should say. And yes, we're just trying to make this scene sing when it comes to the lighting. So yeah, we're getting there one step at a time. Yeah. So that's why we're studying the lighting here and digging in and writing notes. Per unit area. Thank you. I appreciate that. So yeah, we gotta make this make the lighting look real good. You know. Let's get some water. Okay, so the next definition, luminance, not imilluminance, which is... So what is that? What does that mean relative to the other things? What does luminance mean? I think it's... Okay, Wikipedia. Let's say. So luminance is a photometric measure of the luminous intensity per unit area of light traveled in a given direction. Ah, I see. So this is so luminance is more like light traveled, which is good. So luminance. So illuminance is how it interacts with the surface. Luminance is how it travels. Is a measure. It's a bit like Homeworld. Oh yeah, you can say that. Yeah, I can see that. It's still in the early stages, admittedly. So there's going to be more stuff in the scene once we've got the lighting working anyway, to the level I want it. It's not going to be a mega game or anything like that. It's going to be like a small style arcadey type game where you can just, you know, float around, explore, maybe do stuff as well, depending on what I want to add. The reason I want to do that is when I make my game engine, actually make a game and then slowly improve on that, right? So we don't want to make the there's like a meme, right, that people say like the last thing I want to do is follow the meme of I want to make an MMO RPG where your choices matter, you know, that kind of silly, like that's like too intense, right? I'm not trying to make a game engine that can do everything. Of light traveling. So yes, make sure that we can actually finish the thing by my lonesome, and given that, we'll get some hopefully something out there for you guys to play. Anyway, the lumens is a measurement of luminous intensity per unit. Okay, fantastic. Again, that's also why we are measuring oops, which one measuring? Yeah, measure ing. Good, you are practical rather than pretentious. Yeah, 100%. You know, I only have a certain amount of life in this world, and I can't spend it on making one game that will be subpar anyway. If I just end up making one game, rather than make, you know, I've got to make a couple, at the very least, you know, at the very least, per unit area versus traveled. Right, okay, so we got that done. Next is to figure out, I think the rest is pretty straightforward. I just want to make sure that everything's good. So candela, lux, nit, watt, lumens per watt, and luminous efficiency. So this is I think what we get here, the other two are tied to each other. So I think that's pretty self-explanatory. So let's keep on keeping on. So where are we? Where is our buck? Nope, that's not what we need. Are you from the USA? No, I'm from the UK. Where are you from? Just watching. I assume based on the currency, you're from India? I think that's a rupee symbol next to that. From your very kind donation. Which is always nice to have people from India checking us out. Yes, jolly good. Alright, so I'm going to read this paragraph and get further into what lighting is and how it works. Okay, so to get properly coherent lighting, we must use light units that respect the ratio between various light intensities found in the real world scenes. These intensities can vary greatly from around 800 lm, which would be luminous power for a household light bulb, to 120,000 lx, which would be lux, which would be illuminous for a direct sunlight. For a daylight sky and sun illumination. The easiest way to achieve lighting coherency is to adopt physical light units. This will in turn enable full reusability of lighting rigs. Using physical light units also allows us to use a physically based camera. Okay. Right, so table 10 shows light units, shows the light units associated with each type of lights we intend to support. You can put a rotating pulsar in the background. Yeah, that would be sick. You know what I mean? Like that's what I'd be. That's what I want to add. Like kind of cool space stuff. Even if it's not related directly to gameplay. One thing I've got in mind is space dust at the very least, right? You know, because when you're flying through space in an asteroid field, you're gonna have not just big rocks, but you know, small dust all over the place due to collisions. So. Yeah, I'm thinking about all this type of things, and lighting is very important for that interaction when we have, you know, things working for us. So, lighting types. Okay, so we can have. So it's a good idea to make sure your lights map to real world lighting, real world light units. Here is a table. Again, we'll just type this out. Of different, of common lights, and the units. Here's a table of the common lights and the units you should try to use. Have you read different graphics books before, like real-time rendering? I haven't read that one, but I heard great things. I have another graphics book behind me. I have, obviously you can't see it, but I'll read it out. It's called Foundations of Game Engine Development, Volume 2 Rendering. And this book is basically going over the stuff that we're reading right now, by the way. With the, I thought it would be better as a live stream experience for me to find resources that aren't a physical book. So I'm trying to, so otherwise it'd be kind of a boring live stream. Because no one would be able to see. Yeah, space dust would be amazing, but GPU intensive. Well, there are ways to simulate that. It's you basically fake it with fog, and if I just change the colors and the intensity of the fog a bit, then we actually have some kind of like, you know, space-like looking stuff. But so I'm gonna try and use techniques like that to reduce the. Why don't I stream on TikTok? I've actually never used TikTok, so I wouldn't even know how. Yeah, that's that. I think I like YouTube, so I stream on YouTube. That's pretty much why I stream on this platform. Because when I watch other streamers, I personally like to watch them on YouTube, even over Twitch. Just because Twitch is a bit of a faff for me. To actually use, and YouTube's fine. So yeah, hopefully it answers your question about why I'm on YouTube versus other things. So directional lights. So this is the thing I have at the moment. I have a basic directional light. YouTube has the nicest people. Don't switch to TikTok. Fair enough. Yeah, I wasn't planning to, but not my cup of tea. I don't want to get sucked into short form videos and not make any progress on my game because I'm watching TikTok videos all day. So that's my goal here. So frac, oops, I haven't put this in the brackets. So for directional lights, which I'm pretty familiar with, point light I know how to do, spotlight I don't know how to do, which is very important for a spaceship, I think. We at least need a, if it's very dark at least, some kind of light that goes outwards. There we go. I would say that TikTok audience will be more active. Also, your reach will be higher, but your choice. It's not. It's fine. It's yeah. Don't worry about me when it comes to stuff like that. I will say that I will look into it. You know, why not? I mean, I didn't even know TikTok had a streaming option, but for me, honestly, mostly I just kind of like the simplicity of YouTube. So despite me being a very small streamer, I do appreciate the community that comes about through YouTube a lot. You know, the media. I you know, are really nice people on YouTube, like Monchi has said. So Spotlight is Luminous Power. Okay, so we just can copy this again. Luminous Power, LM. And photometric light. Okay, so that's a new one. Photometric light. Will you produce your own music? That is something I might reach out to other people. People have wanted to work with me, but I need to make sure that when I go to reach out to people, maybe to pay them, or maybe they want to do it for free, who knows, that I'm in a state where my game is closer to done. Due to the fact that I don't want to change stuff drastically and then ask people to make art and music again. So yeah, it's that's my current approach. It's like get as far as I can with the actual game until we need art assets that are serious, and like models and stuff like that. And then I won't you know, accidentally end up kind of, oops, don't need both, I just need this. Then I won't like have to pay / make an artist do things twice, or 3 times or 4 times based on a change I've decided to make. And image-based lighting, image-based light. Maybe you should use Lyra in Gemini. I've heard it's amazing. Is that for music? Yeah, I'm not a big fan of AI specifically, but you know, if I'm pushed against the wall, maybe I would personally, I would, if someone my goal with this game as well, obviously, is to make a game that you guys enjoy, but outside of that, it's also to make an artist / musician, their music to stand out, right? So my code is to facilitate an experience for you guys to play, and I want the art and the music from someone to really shine in my engine. So that's like a big goal of mine. That's why I might not end up using AI at all. I don't use AI in code, at least, anyway. Because I think it'd be really cool, right, if we had like a cool artist. Like there's some music I've heard that that's really inspiring, that I would kind of like to put in the game to set a particular mood. I can't go into that because it'll be a bit of a spoiler thing. You can conduct Lyra like in Composer, but your call. Oh, interesting. Okay, yeah, I'm just unfamiliar with AI as well. It's more for fun, not using AI for anything. Yeah, it's more fun, I think, as well. I'm just not a big AI guy. Other streamers might disagree, but for me, that's what I like to do. Anyway, let's read this. Notes on radiant power units. Okay, so even though commercial available light bulbs often display their brightness in lumens on the packaging, excuse me, it is common to refer to the brightness of a light bulb by using its required energy in watts. I see. The number of watts only indicates... Okay, so the number of watts only indicates how much energy a light bulb uses, and not how bright it is. It is even more important to understand the difference. Understand this difference. Difference now that more energy, now that more energy efficient light bulbs are readily available, like halogen, LED. Okay, cool. I'll skip writing notes on that particular thing. However, since artists might be accustomed to gauging a light's brightness by its power, we should allow the user to use power units to define the brightness of a light. The conversion is presented here. Okay, so So if we want to use watts to work out light. Sometimes Gemini forgets what date it is. Oh, that's funny. I don't know why the AI would forget that. Oh well. I could do lots of complicated things, but I can't remember the date. Interesting. If you want to use watts to work out with light brightness, light brightness, I'd just say brightness, you can use this formula to go from lumens over watts to lumens. Go from lumens over lumens over watts to just lumens. Okay, so this is very straightforward. I'll just copy this out because I'm not saving anything by typing this out really. Whoops, my bad. Sorry about that. Paste. Nice. It has training data. It has to do with training data. Interesting. It goes back to 2024. And it says RAM is cheap. Oh no. That's depressing. Yeah, that's not valid anymore. Okay, so in equation 52, eta is lumens efficiency of a light expressed in lumens per watt. Okay, so eta backslash is luminous efficiency. Luminous efficiency. Efficacy. Efficacy even. No. I'd say efficiency of the light expressed in lumens per watt. Fantastic. Alright. Oh well. Maybe we'll get back to that RAM being cheap one day. Alright. Maximum possible lumens efficiency is the maximum. I don't really know what this means, but I don't think it's too important as long as I make sure that I'm understanding this a little bit. Because currently we don't have a coherent unit system in my engine, so this might be something I implement. It might not be, but it's good to know regardless. Because if I want a particular type of scene in the future, this will be like a good so 683 for a reason that I don't understand. We can also just use V, also called luminous coefficient. Whoops. Let's try and type out the words correctly. Yeah, I hope in the future with RAM that companies end up let's grab that as well. Like who make RAM just decide to take advantage of the fact that everyone needs it now, and just make loads of it. That'd be a good future to have. Because I have been putting off making a new computer for that reason alone. I don't want to get ripped off with RAM prices. Okay, so this table can be used as a reference to convert watts to lumens, and using either luminous efficiency or luminous efficiency. What? Right, okay, let's just get this word right because I keep saying efficiency twice.
Efficacy.
I thought it was efficacy. Okay, so luminous efficacy or luminous efficiency are various type of lights. Sometimes I just forget like random words like that. More specific values are available on Wikipedia. Okay, so I'm going to skip that and just say, okay, look online to work to learn specific lighting efficiencies and efficiencies. If you're using a coherent ENT lighting system. It's power conversion, I think. Number of photons per watt. Yeah, that makes sense. I think that's pretty much it. Yeah. So, that's what it. I see. You're explaining that. Thank you. I'll write it down actually. So this is. Let me write this down. As this is a power conversion using the number of photons. Yeah, because it didn't explain this, did it? Per watt. Nice. Okay. Fantastic. All right. So we have that written, and I'm going to make this into its thing. I'm going to say lighting units, basic lighting units. So this is what I call a source node, and I need to make this into a small one. So in the future, lighting units, unit lighting or lighting units? Lighting unit basics. It's not complicated. Let's just keep it simple. So this is a tool that allows me to connect knowledge that I already know to other knowledge, and this is why it's really powerful. So I split these up into small little readable chunks like this. Graphics theory, is that lighting theory or something? Yeah, light theory. So for example, I'm able to go, okay, so basic lighting units is very similar to the stuff I learned when I was talking about, if I go to graphics theory, which is where everything is listed in an index. So I can go, okay, yeah, light distribution is very similar to what you just discussed here. And now I can say like, okay, so when I read about lighting distribution or reread about lighting basics, I can check out lighting distribution to have these ideas connected. So that's what I'm doing here when I'm filling out this. It's so in the future I can basically never ever have to read the this ever again. I can just refer to my own notes. In the long run, in the short term, this is definitely slower than just like reading a book from start to finish. But in the long run, all these things will become useful and help me make better graphics and things like that, right? Because we're in graphics theory. There is Vulkan here, which is a lot longer. It goes on and on and on. So there's a lot of Vulkan stuff. So yeah, that's what this is all about. And I just need to list. Yeah, I already listed that. So this is why I'm writing things. So this is the. We'll continue on with this. Like ready reckoner. What's that? Is that a thing? Is that actually don't know what that is. Right. Okay, so yeah, pretty much it's just like it's called a second brain. I know it seems weird to say that. I mean, like a cheat sheet. Yeah. Yeah. So it's like the idea is a second brain almost, right? Oops, not that. Let's close that. How do I close you? Let's go away. So just for the people who've never seen this before, this is like my graph of knowledge. And this is like expertise is built up in the connections of ideas. And yeah, this is the idea is like I connect a bunch of things together to build up expertise in different things. So yeah, that's so I can go from like learning about how to align structs better to updating things in bulk, follow this all the way through to here, and then end up in learning about swap chain color space. You know, that eventually these connect together through these nodes. Yeah, it's a cool technique, isn't it? But anyway, let's continue writing notes, and I'm gonna say this is gonna be to. Okay, so I'm gonna read this. Light unit validation. One of the big advantages of using physical light units is the ability to physically validate our equations. We'll use specialized. We'll use specialized devices. Oh, sorry. We can use specialized devices to measure 3 light units. Okay, so let's just say what is this going to talk about? So I'm going to say this is to do with measuring light. So let's say measuring lights basics. Fantastic. Okay. Okay. Lights. So one big advantage of using physical light. Okay. So yeah. So one advantage of using physical light units is that we have the ability to validate our equations. Right, cool. Okay, so this might be more interesting than anything. More than useful. So 5.1.1.1 illuminance. This is a device. This device is used in movie sets and camera shoots. So you are mimicking that mimicking it in a GPU. Ah, okay, right, cool. I did not know that. Thank you for thank you for just watching. Okay, so illuminance. Right, let's continue. The illuminance reaching a nothing to worry about. Okay, so my window just slammed. The illuminance reaching a surface can be measured using an instant light meter. For our tests, we use a this thing shown in figure figure 33. The instant light meter uses a white diffused dome, I see, to capture the illuminance. For a moment. Yes, can I just I'll have to respond to this. Just a phone thing. Yeah, someone just text me something. Yeah, so I'm just gonna yeah, so something important's come up. It's nothing serious. Just need to respond. If you want. So yeah, Apologies for this. One moment, it's nearly done. All right. Cool. Right. So the diffuse dome. Let's see. Depending on the desired measurements, for instance, orientating the dome perpendicular to the sun on a bright, clear day, it will give a very different result than orientating the dome horizontally. Makes sense? So that would give us what? This is giving the... Based on this picture, it's giving a reading in... Is this in lumens, or... What is this? What is this measurement? Or is it the other one? Give me a moment. I'm just going to scroll up my notes. I should look at my own notes here. So this is the... one moment again. Chill. Okay. Fantastic. Right. Sorted. Okay. So, what is this? I'm just going to move on with that. Oh, it's the... idiot, it's the title. So that is the... It's measuring luminance, so how much light is... the intensity of the light source when it hits something. Got you. Okay, so luminance. The luminance at a surface or product of instant... is it... Well, the product of instant light and the surface... The lumens at a surface, or the product of instant light and the surface, can be measured using luminance, a luminance meter. Luminance meter, okay. Often called a spot meter. While often called a spot meter. While instant light meters use a diffuse hemisphere to capture light from all directions, a spot meter uses a shield to measure instant light from a single direction. For our tests on this thing, we can place the diffuser on the L478D to measure the luminance at a cone of a degree of 5. I see. Okay, so... right. Okay, so this is what this is measuring. This is the distance traveled through something. Okay, that makes sense. Okay, so the luminance intensity. The luminance intensity of a light source cannot be measured directly, but can be derived from measured illuminance. Okay, if we know the direction, if we know the distance between the measuring device and the light source, the equation 54 is a simple application of the inverse square law discussed in 522. Okay, so how much do I need to actually know of this? Candel units. Yeah, it's I think that's right. Yeah, I think that's Candel units. That's exactly right. If I look at my thing, right? Oh no, it's no, that wouldn't be right. That's lumens. Oh, this is. I think this is the luminance intensity. Yes. So this is Candel units. Yes, this is Candel units. Um. Everyone. So we have so what do we have? We have a direct light. Okay, so let's write this down. So candle units per square, 5 degrees. Right. Okay, so let's write that down. Yeah, that's actually kind of useful. So yeah, so candle units per unit squared. Okay, so let's see the photometer. Yes. Okay, that makes sense. Okay, thank you. Thank you. Just watching. It's always nice to have someone in the live stream and help me out like this. It's very much appreciated. All right, so no problem. Appreciate you though. So right, let's write this down. So we have a. This is Candel. Candela. Per meter. Oh, sorry. When we are talking about. We are talking about measuring lumens. I should bold this perhaps. Not this. I should bold this. The word "this" came up. Oops, keep pressing the wrong letter. And so we need to figure out. Okay, so we are measuring the candles per. What is it? Candles per meter squared. Fantastic. Okay, so meter squared. Which intersects with a point at with an on a plane with a strident cone. Strident cone of 5 degrees. So I'm gonna write that. I'm gonna probably take a picture and kind of like explain this a bit better. Oops. Let me think for a minute. Right, let me just... Is an angle measured in 3D... Oh, okay. Which is an angle measured in 3D. Right, thank you for that. Sorry, I'm just still... this person needs my attention again. Just bear with me. Don't know... Okay. Alright. I'm going to do that later. Okay. Right, fantastic. Okay, now let's try and reconcentrate. So, my measuring candle user permits its segment of the plane, strident, stridian, angles measured. This is likely. Sorry, this is used when we need to work out sorry, that this can be used. It's the eye. If I look at my eye, yes. Okay, so you can see this done in this picture. Fantastic. Okay, so if you scroll up and grab that. I think I've already got snip open. And let's grab this. I think I don't need the whole thing. In fact, I'm gonna, just to save a bit of space, because it's a massive image. What I'm gonna do is just take the screen, which is just kind of like the general idea. So, measuring tool. Is a tool for lumens. Sorry, luminous. Sorry, luminous. Alright, that'll do. That's fine as long as it's not called image 1. Doesn't really matter. Okay, so, alright, let's move that. Sorry, this is all light physics, so raster copies the real world to create realism again. Yeah, pretty much. That's what we're trying to achieve, at least. Yeah, thanks for bearing with me, guys. It's, yeah, sometimes real life gets in the way of streaming. No, but we need to deal with stuff like that. Anyway, so with this, we can work out the intensity of light when we do using the inverse of the inverse square law of light when we sorry, if we know the difference. Alright. Okay, so we just write this equation out, and it is I equals E C dot D to the power of 2. Okay, so here we go. Directional light. This is what we're after. Alright, so I'm just going to throw this into a... I don't think we need anything else. When we talk about lumens, we are measuring candle units per meter squared, which intersects a plane with stridian, which is an angle measured in 3D of 5 degrees in this picture. Below, I think I can get rid of that other line. Let's just clean up my notes a bit. Yeah. So with this, we can work. Yeah, we can work out the intensity. So I think I'm going to say, a quick note to myself. This might not be as important as just matching the real world to get nice, accurate lighting. Because I was thinking about this, right? Just then. This is nice to know, but I don't think it's that important in general. I think it's just a general nice thing to know. So measuring basics. So it's measuring light basics. So measuring light basics. So let's create this into a small little section so we can look up this later, which will be nice. And okay, so we do this, graphics theory and lighting theory. We add this to our lighting basics and do this. And what do we want to do? We want to connect our lighting together. Lighting basics, measuring light basics. Let's connect this to there. So we connect these notes together. So we just need this to connect to that. So I can find these notes, connect my knowledge, grow my knowledge, so we can become a better programmer. That's the whole goal. Graphics, oops, that's graphics theory. We need that. This is our index, like a book. We throw this in here. Fantastic. Okay, so one moment, once again. Thank you for watching, by the way, guys. I very much appreciate anyone who's liked and contributed to the stream. Obviously, just watching. Thank you very much to you as well for that previous donation. But I very much appreciate everyone who's even if you're just lurking. I just want to say thank you for joining in with these streams. I honestly thought that no one would even watch these, and it's honestly repeated it's repeatingly nice that people are interested in what I'm doing. So honestly, you guys are owe you guys much when it comes to this, keeping me motivated and keeping me doing things. So yeah. So yeah, just let me text this person and I'll be right back with you. Oops. Yeah, just a little bit longer. Yeah, just a bit longer, guys. Sorry about the but yes, family stuff, that's all. You know how it is. You know how it is. Okay, so let's dig into this a bit. Let's run this. Let's run this engine and see how the lighting works when, like, how bright and dark things are. Because I need to make sure that when I'm flying around, I guess, that we have kind of like stable. Because the thing I don't quite understand is why is everything so specularly lit, and the diffuse lights. So as you can see, everything's quite dark, so I'm just going to fly around trying to figure this out. Because something I don't quite understand is when I'm flying around, at least, like, why does everything kind of, like, flicker like this? It kind of looks cool, but it's kind of like, it's a bit too flickery, if that makes sense. Like, it's like too specular. So if I keep moving around, so I was just looking around. So if I spin this around a bit, oops, sorry. So we get like a bunch of light over there, but not much light over here, which is confusing me. We only get like, because I do have emissive light in this. Right, so... Right, there we go. Okay, so, what I'm going to do briefly then is just reduce the reflectance equation down. Because I think this. Although I said this kind, I want my thing to. I want sorry, I want my lighting to be more accurate. Yeah, and thank you for bearing with me there, guys. I have a sneaking suspicion that I lose a lot of diffuse light with that equation that I used. And if I increase if I get rid of this, like, and just use luminance, just the strength, right? I'm trying to just bring up the diffuse light of the scene. Yeah, okay, so the occlusion, the occlusion of the scene was causing a lot of darkening. And I think the diffuseness is, the speculousness has been reduced. I think if I reduce the intensity, so 50 maybe, and increase the base light to 2 perhaps. Okay. We might get like some. Okay, that's a bit better. Yes, less flickery. I don't mind the flickeriness because that's actually what light would look like, I guess. If it was reflecting off ice crystals, right? But when we get closer, when we get like further away, it gets a little too extreme. Alright, so let's get into the directional light stuff, because that's something that we need to do. Do you have MIPS? I assume it's texture sampling issues that's causing the temporal instability. Let's have a look. I think I do in my textures, but that's just yeah, I think I do. I actually definitely do. Let's go to our lighting. Sorry, this would be in the GPU device, in the big Vulkan header, right? Oh, wrong thing. So this is my big Vulkan class, which basically has 80% of all the Vulkan code. Where's the texture stuff? Texture is create texture. So, oh no, this is a pre-MIP map, but at the very least you can see I'm setting up a MIP value here, and when I do a create texture, just work backwards, we go into here and then create texture. If I find the, oops, sorry, that's my Windows noise, not yours. And if I go to, where is texture used? I can't, what's the, there's like lots of functions. Let me just see the call hierarchy. Let that load for a second. Okay, so create cube map and load model. Okay, so in here, yes, we are taking, just to show you guys anyway, we aren't using any KTH stuff at the moment, but we are building up a MIP chain of different textures, sending that in here with the destination sample as 2 flags. This is just the MIP level. So we are sending stuff in, and the thing that I just think it's the specular lighting, to be honest. I think it's just too aggressive with the specular lighting. I can't touch this. Because it doesn't happen on other models, like the ducks, for example, wherever they are. Just flown away from them. But I could be wrong. Hang on, let's turn it off. So I have, let's see. Oh no, it is a bit. I don't have any anti-aliasing, maybe? No. I've made these ducks metallic for now. But you can see, yeah, it's one of the things I've been struggling with this engine. So yeah, that's what I'm thinking of anyway. So guys, I'm gonna get my lunch now. What I do in this case, if you're new, I stick on a video so I can chew and eat without you guys having to hear me chew and eat, which would be gross. So I think what I'm gonna do is go on to a for some reason I'm getting recommended this. Watch this if you feel too much. Gentle comfort for tired women. I'm not a tired woman. Yeah, so I think I'm going to put on some Oscar. Unless you guys have any recommendations. I think this should be kind of... Let's find something that's like good. Like a good long... Right, so let's see, what would be good? Yeah, because I don't want to hear, I don't want you to, I don't want you to hear me chew and stuff. And I want to keep going, so, what I'll do is I'll how Shrek revolutionized video games? They're a bit short. That's the only question. I need to be able to eat and be educated. Let's see. Hey, how you doing, dude? Just about to pick a video. Help me land a job. It's tough out there. I'm in the same boat. So it's so I can't really help out that much, to be honest. So let's go with no, that wasn't. That was a. Yeah, kind of. Yeah, I'm a software. I was a software engineer for 6 years professionally. I wasn't a graphics programmer though, so some of the stuff you may be thinking like, "Whoa, he doesn't know this." Yes, the graphics programmer. We did a lot. I worked in the CAD industry, which is different from games and graphics. Really, CAD can be very graphics heavy, but not what I was doing anyway. So let's pick. Let's just go to my resources actually, and check out a decent video. So I think what we're gonna watch. I have a temptation, let's just have a look, to start, maybe not watch all this, but the data-oriented design of C++. I think I watched some of this and it was really good. No, actually I'm going to watch, because I already watched it. I just realized I watched some of this because I was watching it on stream, so I don't want to watch, I don't want to let people damn, I'm struggling to think of a video right now. How about we watch some of the legendary? Would help really good. I can give you some general advice, but general advice would be make sure your GitHub is up to date and frequently updated, and on top of that, make sure that your make sure your CV is good. I would recommend if you know someone in the industry, have them look over your CV and make sure that's good. We call CV a resume. If you don't know what I'm talking about when I say CV. Obviously, that's really basic advice, and every programmer kind of knows that kind of stuff. But that's what I'm doing, generally speaking. So I'm gonna mute. I'm gonna make sure this audio is good for you guys. And on top of that, I am going to send this up to about 70. Yes, it's up to date. Okay. Yeah, it's tough out there. It's honestly really tough. CEOs have become a bit deluded with the AI. And so they think they can replace everyone, including their mother, when it comes to programming. So I'm going to stick this on. This is on a Senemal. Like, this is one of the best talks CPP Con has ever got. And it's about data-oriented design approach to C++ programming. I wish you the best, honestly, with your job search. It is tough out there. And I think it's going to be a great, like, fun thing to think about as we develop our software. Anyway, so, yeah, I'm going to stick this on. I hope you guys don't mind me just it takes me about 15 to 20 minutes to finish some food. So I will finish that, and I will do that. Sorry, I will watch this video, eat my food, and get back to you as much as I can. Thanks, mate, absolute legend. I appreciate you, dude. I appreciate you honestly turning up. That's why I want to give you the time of day, and yeah, I wish you the best, honestly. All right, so I'm going to skip into this a little bit because he kind of talks about himself for a bit. So for those who don't know who Mike Acton is, he's a top tier programmer, right? There are programmers out there who are just better than every single other programmer, and he's in that group. He was a game programmer when it was really difficult to be a game programmer, back in the 2000s, and he rose up through that difficult time, back when everyone was interested in true 3D like Quake and doing things like in Half-Life. Like, in between that era, it was very difficult to be a game developer studio and work on because you had to do 3D graphics before we had graphics cards, right? Can you imagine how difficult that would be? Like the maths that you had to do, the software rendered 3D engines were very, very difficult to do. So he rose up in that group that all got good at the same time. And at this point, he worked at Sony as the lead principal game engine architect. And he's worked on Unity for a long time, and I can't remember, he's moved somewhere else now. But in this talk, he's talking about how you should write real-time applications when it comes to like game engine stuff. So honestly, I've watched this multiple times. I think it's one of the best talks out there in CPPCon. So yeah, I will mute the stream and get my food, and yeah, hopefully we can watch this, and I'll be right back. As I'll go to push to talk. I'll still be able to talk with you guys if you do ask questions and stuff. Just be aware that, you know, I will be mostly quiet for this period, so you don't hear me chew, which would, you know, be horrible to listen to. All right, enough rambling. This should be loud enough. Let's see.
And that's critical to us. We have, you know, we want to solve new problems, and in order to solve new problems, we have to make space for them. And as I said, we have that window in a frame that's 16 milliseconds or 33 millisecond space. And so if we want to put more stuff in there, we've got to make space for it. Performance is king. Maintenance in general, you know, we have to maintain it. We have to continue. We have multiple games in flight. We continue with the development of the engine and tools over time, over games. So we have to make sure it's maintainable from our point of view. Debuggability, again, we don't, you know, we have hardship days. We have to make sure that we can solve problems, you know, right before gold, you know, right when everything is coming together, that those things get solved quickly. So being able to reason about what's gone wrong is crucial to us. What languages do we use? As Alex said, the industry is dominated by C++, and that's no less true for us. But we do use a lot of other languages in the mix, a little bit of C, a little bit of assembly, Perl, JavaScript, C#. Obviously not all of these on the actual console target, but on our PC development side. I'd say for our whole code base, C++ probably represents about 70% of our code base. That's a rough estimate. I didn't actually count lines of code or anything. Certainly our most preferred target would be assembly. Like, that would be the thing that we would love to just work in all the time. But reality, of course, means that we use tools that help us do that rather than doing it directly for all the things, especially at scale. There's also...
Yes, I just got my salad. See you in a minute.
Random other things, pixel shaders, vertex shaders, all that sort of GPU stuff, geometry shaders, compute shaders, a lot more work going on in this space now. And to connect with the keynote yesterday, we definitely don't make games that go to Mars, but there's a lot of similarities between what we do and what I understood that that JPL did in their embedded system for the rover. So how are games like the Mars rovers? Exceptions. In a similar way, we avoid them. We turn them off if we can at all help it. Occasionally there's a third-party library, some other third-party code that we have to interact with that's designed around them, so we'll sandbox it off. Templates, while we don't have a hard rule that says no templates, we do have I have a particular face that I might give someone if they use one, and it's not a happy face. So there's occasionally a good use, but most of the time what it is a poor use, and most of the time it slows things down. Certainly anybody who's worked with templates at scale, or a code base that's heavily relied on them, knows how it cripples compile times. IOStream in particular, while we do use the standard out mechanism for our sort of TTY and debugging info on the console as well as on the development PCs, we don't use the C++ specific implementation IOStream. Multiple inheritance, that's right out. That's not even a question. Like, that's just dumb. Operator overloading. So we don't, again, unlike the JPL project, we don't have a strict rule about no operator overloading, but you will get the frowny face or the angry face, depending on how complex that overloading is. For a rule of thumb is if it's super obvious what you're doing, we tend to let it go. So adding a couple of vectors, it's super obvious what that's going to get transformed into. Okay, we'll let it go. But anything sort of significantly more complicated than that will be heavily frowned on. Runtime type information, that's off the table. We definitely don't use STL, to go back to the question of templates and compile times, but also because we found, generally speaking, it's not that we have a replacement for STL that we think is somehow magically better, it's that it doesn't actually solve the problems that we want to solve, and we want to solve the problems we have. Custom allocators in the same way. We don't have a sort of general dynamic, we don't use the general dynamic heap management. We allocate all the memory up front. We divide it into sort of a set of hierarchies, then each sort of sandbox manages it.
You can probably see now where a lot of my inspiration comes from my engine, which is in the description if you do want to check it out. I'm very much trying to follow these principles when it comes to writing my own engine. Very much inspired by the Sork and Mike Acton and all the data-oriented design people out there.
Data in its own way that's appropriate to its system. So we have tons of custom allocators that will work inside those sandboxes. Some of them, maybe that sort of familiar kind of heap management inside of a sandbox block. Some may be small block allocators. Some may be sort of linear allocators for systems that just need to sort of linear burn through and then reset. We have tons and tons of different things. Custom debugging tools, again, back to debuggability. We have a lot of tools that sort of introspect into our data and either pull it over to the development PC from the console so that we can examine it. We have tools that do examination live. We have tools that do examination offline and sort of dump a bunch of data so that we can analyze it. Tons and tons of debugging tools. So in a lot of ways, because the Mars rover project is a very small embedded system with very limited resources, and certainly a console at the scope of PS4 or Xbox One is much, much bigger by comparison. They share a lot of similar properties, right? They are these sort of fixed resources, and you want to take advantage of those resources. So in that way, we end up at a lot of the same places. So back to the title, this data-oriented thing. What does it mean? Is it even a thing? Is it like is it a process? What does it mean? So I want to talk, when I say it, I want to talk a little bit about what I mean. And fundamentally, this is something that it's just a fact, right? It's not a belief. The purpose of all programs and all parts of those programs is to transform data from one form to another. Physical fact, that's the point. But this is sort of the reminding principle of why we're doing what we're doing. And to that end, if you don't understand,
you can think about that as like getting an image and displaying it in your game engine, for example, through a texture.
Understand the data that you're transforming, right? You don't understand the problem at all. Conversely, you understand a problem better by understanding the data that you're working with. And different problems, this should be obvious, require different solutions, right? Everybody should agree with that. So if you have different data, you have a different problem, right? Which require a different solution. If you don't understand the cost of solving the problem, you don't understand the problem, right? If you can't reason about the cost of the things you're doing, you don't really understand the problem. If you don't understand the hardware, you can't reason about the cost of understanding the problem. Every piece of hardware, every imaginary set of hardware that you're going to be working with is finite and has some range of performance characteristics. And that's the only way to consider how you're going to solve it, is to consider those characteristics.
Like with lighting, for example, do I want to support ray tracing? Like that's the type of questions you should be asking if you're writing this type of software yourself. Because other people won't have ray tracing graphics cards. And so how do you support that type of hardware, It's also the case that you don't want to support hardware that goes all the way back to the first ever graphics card that ever existed, the Voodoo 3D graphics card, right? That would be silly. So you need like a bound of where your software needs to live. That makes sense for you and your use case. I just love all this. It's so good.
Characteristics. And everything universally is a data problem, including usability, maintenance, debuggability, etc. Everything is a data problem. It's not a code problem. And solving problems you probably don't have creates more problems you definitely do.
This still trips me up to this day.
So avoid adding problems to the space
that still trips me up to this day.
And you know what problems you have because you have analyzed the data. And latency and throughput are only the same in sequential systems. And just some rules of thumb. Where there's one, there are many. So, as a rule of thumb, you look in the time axis if you can, and you solve the most common problem first, which is, I have a bunch of these things that are definitely going to happen over time. That's the most common issue. That's the one I should manage, as opposed to trying to imagine that, this one thing exists in a vacuum. Rule of thumb, the more context you have, the better you can make the solution. So don't throw away data or constraints that you need. You want to know more about where something is going to be used, how it's going to be used, what data is acceptable, what ranges are acceptable in order to make an appropriate solution. And I think fundamentally for us, this sort of concept, this non-uniform memory access concept extends over time for us as well. Where it's not just on the console, but the data that's on the console also, we conceptually view it as extends to, the hard disk of which would be read, and the Blu-ray which will have served that, and then back to the development PC. That data got built from a source data, which was then built from Maya or whatever, or our development tools, all the way back to the original artist with the mouse, right, or keyboard. So there is this sort of stream of input over time, and we have to manage that entire pipeline and understand the cost of data access throughout that entire pipeline over time, not just this sort of we don't look at it in a vacuum and sort of this individual access at this one point in time. And most importantly, I think, software does not run in a magic fairy ether powered by the fevered dreams of CS PhDs.
It's also true for people online. Sometimes, I've been quite lucky in this case that people haven't come into my chat and told me to write code in a particular way. But sometimes you've got to remember that these PhD people, that they have like a magic, like a perfect idea of what the software should be or something like that, right?
Software's real engineering that runs on real hardware to solve a real problem. And ultimately, reason must prevail. Like if what we're doing is unreasonable for any reason or imaginary, then it has to go. So that hopefully gives you some context of what I mean when I say data-oriented. So is it a thing? Well, it's certainly not. These are not new ideas, right? There's nothing in here that's new or news. It's really just a reminder for me, for others, of sort of those first principles. And reminding us what's most important, concentrate on that, get rid of everything else. But to a large degree, the only reason we're talking about this, the only reason I've ever talked about this, is because it has been a response to the broader culture that C++ has engendered. And most prevalently is what I call the three big lies. And those are lie one, that software is a platform in and of itself. Lie two, that code should be designed around a model of the world, just your mental model of the world. And third lie is that code is more important than data. So lie number one, software is a platform. This should be super, super obvious, right? Hardware is the platform, right? You have text, you have data, goes into some CPU, spits out other data. Like that's the point. Different hardware, different solutions. You have a different set of hardware. The solution is by necessity going to be different. If I have if I'm programming for a 6502 versus a cell versus the ATI 5870 versus some ARM versus some a server farm full of processors, right? x64 processors. These solutions in each case are going to be entirely different because
this includes for web as well. People say that, oh, I don't know what my code's going to run on in web, but there is still a bound of what type of computers it's going to run on. It's not going to run on the first server ever created. It's going to run on a particular platform. Despite all the Docker stuff that may happen in between, there is some ground truth that comes back to it's running on a particular computer.
They're different hardware platforms. They have different constraints, different physical constraints apply. You cannot make a solution independent of the actual platform or finite set of platforms that you're working for. Reality is not a hack, right? It's not something you're forced to deal with to solve your abstract theoretical problem. Reality is the actual problem that you're trying to solve, right? It doesn't make your code less nice that you had to actually do something with actual data on a real actual platform to make it actually work. Like that's the point. That's the thing it should do. So if you think the right way is some way other than the way that actually works in context, then your idea of the right way is wrong. Lie two. Code should be designed around a model of the world. This one sort of has trickled into the C++ culture from that sort of object-oriented space, right? And sort of building up that model of the world and trying to codify that. In that process, hiding data is implicit, right? That's sort of what most people would even suggest is the point of it. But this is bad. It confuses two important things. One is the maintenance, which is a good thing. Like we want to be able to maintain changes to our access to the data. Great. But it confuses that with understanding the properties of the data. What is the data? How does it work? How big is it? What's in there? This is going to be the most important thing that we need to know in order to actually solve problems. And confusing these two things, or confounding these two things, means at the cost, potentially at the cost of slightly better maintenance, we have now made our problems very, very difficult to solve, or at least to solve well. And this whole idea of world modeling implies some relationship to real data or transforms, right? It's as though if I have some model of the world and I codify it like that, that's actually the thing that's happening. But the problem is that in real life, classes of things, right, are fundamentally similar. They really are the same. A chair is a chair in real life. But in terms of data transformations, in terms of what we do, these classes are really only superficially similar. So, in our context, in the context of a game, we have a chair and a physics chair and a static chair and a breakable chair. These things are not at all similar. Like, there's almost nothing that's the same between these contexts, right? How they're handled, how the data is managed, how the data is transformed. There's virtually nothing that is the same here. And yet, the tendency would be, because they share some world modeling similarities, or similarities in the real world, that they ought to be connected somehow in sort of the code hierarchy, which is nonsensical, to be honest. So world modeling in general leads to these sort of monolithic, unrelated data structures and transforms, leading to all kinds of other problems that you shouldn't have in the first place. So from my perspective, I think that world modeling is trying to sort of idealize the problem away, sort of back to there is no software ether that we're running in, that we really need to understand the data and the hardware that we're working on. You can't make a problem simpler than it actually is, right? The actual reality is you have this finite set of hardware. The actual reality is you have this finite set of data. You can't make it simpler than that. And I sort of see world modeling as the equivalent of self-help books for programming. It's sort of like trying to engineer by analogy, or engineer by.
Fun fact: the people who heard this talk really hated it, mostly. No one liked it at the time. There is one person in the audience who comes up and asks a question, and they actually gave another similar talk. So there was a couple of people who really resonated, but most people who heard this talk really hated this part where they were talking, I assume, this part where it's like move away from object-oriented programming, which seems to be like the ground truth when it comes to programming. So
storytelling, as opposed to engineer by engineering, and that makes it, not as good. Lie 3. The code is somehow, for some reason, more important than the data, that we spend so much time focusing on the code. So much time talking about, we're all here, honestly, to talk about the code, right? So much development time and brain power spent talking about the code, when the vast majority of the time, the code is not the real issue. The code is a minor issue in all the things that we work with. It really is the data that we're dealing with is the thing that we are reasoning about, and the thing that's the actual problem. As I said before, the only purpose of any code is to transform data, right? It's got to get it from this form into this form. Whether that, at a high level, it's from like data on disk and player input into what's on the screen and the speakers, and that's sort of hierarchically down to the systems and the things that are transforming data inside the system. And the programmer is fundamentally responsible for that data, right? Fundamentally responsible to make sure that transform happens correctly, happens fast, happens in a maintainable way, not the code. Right? The code is the tool that we use to do the transformation. So the programmer's job is not to write code. And I think people really, really don't want to believe this. Like, it's not your job. Writing the code is not a job. Writing the code is the tool you use to do your job. Your job is to solve data transformation problems, right? Solving the problem is the job. So to that end, right, only write code that has direct, provable values.
All right, gang. Thanks for dealing. Thanks for all. What am I trying to say? Thanks for dealing with me with that and all the family stuff. I appreciate you. Bearing with me. That's what I meant to say. Let me just untangle my headphones, which have got all tangled. Fantastic. All right. Let's try and get through as much lighting code as we possibly can. Hopefully you enjoyed this talk. I highly recommend, if you're interested in writing high performance code, check this out all the way through, right? And just if you don't know, right, you may think like, okay, don't take my word for it. Tokyo Spliff has commented on this video saying, now it's important to watch this one once you wake up and once again before you fall asleep. And if those of you who don't know, he's also doing basically what I'm doing. I just he's got, you know, a lot of subscribers. He's also building like a really good game engine type stuff, right? In OpenGL, and I think he's using Vulkan. I'm not entirely sure what his Vulkan status is, but you know, he's got a lot of subscribers, you know, that kind of stuff. So he's a bit more famous than I am, just a touch. So yeah, it's a really good. So don't have to take my word for it. Check this talk out. It's honestly very, very good. I think I've listened to this literally about 20 times. So every single time I listen to it, I learn something new, right? Even just learning then, it's like, oh yeah, it's nice to be reminded of like how important the data is versus the code. You know, just simple things like that. You know, when it comes to, you know, when we're doing lighting, for example, we're about to start taking notes on lighting again, right? It's like, why are we doing this? Why do we care so much? Why am I taking so long? You know, compared to like, you know, just reading this book, you know, from start to finish. It's because I want to understand the data so well that when I transform it, and actually get things working, right, that we end up in a situation where it's like the transformation happens flawlessly, and that's the idea, right? That's my general goal. So understanding the maths, understanding like what lumens are, understanding illumination, all this stuff is to figure out like the data that needs to be transformed to solve a particular problem. And it's honestly super, super important if you want to become a good dev at this type of stuff, right? I'm not going to say that this is necessary for everything, right? It'll make I have a feeling that it'll make you a better dev in general, but for doing graphics programming, like, oh my goodness, you wouldn't believe how important this stuff is. It's so important. Understanding the data, how to transform it properly. I mean, just look at this, right? So I'm very passionate about that talk because it gets me all passionate. You know, let's look at this. Like, look at the light transport equation. This is the integral that we're solving, right? For every single light beam that touches, right? And this would be the integral over a hemisphere, which would be like half a semisphere. A semisphere, right? That's a hemisphere, semisphere. That's what I used to call them. And this is expensive, right? This is what we're doing. We're taking data that's like a lumen, right, or simulating a lumen, a light beam, and we're doing something, and we're transforming that into a pixel, right, a pixel color. And it doesn't matter how we go about this. We could do ray tracing. We could do, I don't know. We could do it in a very simple way. I don't know, like blind Phong lighting with just Phong lighting, which is a much simpler lighting model. Like, it still doesn't matter. We're still taking data, we're applying a transform, which would be the lighting algorithm, right? This thing, and then we're getting something out by the end of it, right? So even when it comes to lighting, we have this like dichotomy of we are trying to transform the data as fast and as efficient and as well as possible to achieve the desired outcome. So I just love that talk. It's honestly like I'm so passionate about that kind of stuff. So I hope you guys appreciated it as much as I did, and I highly recommend for those who don't know. I'll post it in the chat as well. Let me grab it so you guys can check it out later, right? And let me just throw this in. It's extremely good, right? So I'm just going to throw this in there. Yeah, feel free to watch that. Obviously, you can watch that now if you want. So you don't have to stick around. But yes, give it a go. I think you'll thank yourself in the future once you start to think kind of like in that data-oriented design way. Even if you use object-oriented programming or some procedural method or whatever, having that idea of the transforming the data is the most important thing is gonna be beneficial to you. I have a feeling, no matter what you do, seriously. Anyway, let's pick some. I enjoyed this yesterday. This was kind of fun. Pick some more music. yeah, some Soulsborne stuff. Soulsborne music. Oh, sorry, this music is going to be really loud. I apologize. Let me turn that down. That was probably really loud for you. Yeah, so you probably just got your ears blasted off. I do apologize for that. Let me turn that down for you guys so you don't have to hear that. And let's just check the audio. Yeah, it's still quite loud. Let me just turn that down a bit. Cool. Hopefully that's good. Let's see. Alright, that should be good. That's just like background now. Let me know if that's if you're having, if it's uncomfortable for your ears, let me know and I'll adjust it. Anyway, where's this Kingsfield? Anyway, let's close that. We don't need Cocomelon. I'm not that brain rotted yet that we're going to put on Cocomelon. Anyway, directional light. Let's get this in. Hey, direct light. Direct light. Direct lighting. Cool. Let's get some water. So I'm going to read this out loud like I was before. Now I'm all filled up with food. Yeah, we define... I'm just going to type in chat just for the people. This talk... This YouTube link is the Mike Acton data oriented design DoD talk. Just so people can see it, right? Alright, cool. You know, just because I'm obviously going to not talk about it and people are going to be like, what's that YouTube link? I can't just, anyway. Direct lights, direct lighting. We have defined, so I'm just going to read this out and take notes and try and simplify things for myself. We have defined light units for all the light types supported by, by the renderer. In this section above, but we have not defined the light units for the result of the lighting equation. I see. Even if you have measured carefully all the lighting measurements even if you've measured carefully all the lighting units, there we go. Let me just check something real quick just before we keep going. Nice. Okay, so that's all sorted. Even if you have the lighting carefully of all the lighting units, you still need to convert things to make sense for the rendering equation. Oh, I say rendering equation. Oh no, for lighting. Oh, yeah. For the different light equations, which aren't rendering equations. No, that's questions. Equations. Fantastic. Okay. Choosing physical light units means that we will compute luminance values in our shaders. Sounds good. And therefore that our light equations will compute the luminance out, or radiance, at any given point. The luminance depends on the illuminance and the BRDF. Okay, so when we are computing lighting, we compute the luminance values in our shader, and yeah, for any given point. The luminance depends on illuminance E, and are bidirectional. Oh, he's using the scattering version. Okay. I'm going to say both. BRDF or the BSDF. BSDF. So the BSDF has a transmission function to it, which means that we have the BRDF plus the transmission function. And it's a little bit more complicated to write. Okay, so directional lights. I see direct light. So direct light. So this is the thing we have at the moment, but I don't think it's very good, the one we've got. Right, let me just grab some water. Okay. So directional light. I don't know if this is going to be a whole thing, but I'll kind of combine them together. Directional light. Okay, so this song is so good. The main purpose of directional light is to recreate important light sources for outdoor environments, such as the sun or moon. Okay, so the point of directional light is to simulate the environment outdoors for light from the sun and moon. While directional light does not truly exist in the physical world, any light source sufficiently far away from the receiver, I'm going to say, can be assumed to be a directional light, i.e. all the light rays are parallel. So yeah, light sources far enough away and bright enough / bright enough. I'm going to combine these together, I think. Turn into basically directional lights, where the light rays are parallel. Right, okay, so I don't really, okay, so the interaction between a directional light and a surface, The light source is a virtual construct that can only be represented by a direction. Fantastic. Let's go. Okay. Excuse me. Okay, so let's keep reading. Because we got to get better. It's the only thing that matters. Okay. Oops, I haven't started the timer. Okay, so there's a bit of waffle. So it's not even appropriate to... This approximation proves to work incredibly well for the diffuse response of a surface, but the specular response is incorrect. Okay. The frostbite engine solves this by treating the sun's directional light, as a disk area light. However, our tests have shown that the quality increase does not justify the added computational cost. Maybe for us it would, but I guess not always. We earlier stated that we chose a illuminance light unit of lux for directional light. This is in our part due to the fact we can easily find illumination values for the sky and the sun online or with a light meter, but also to simplify the luminance equation described in 55. So what's E? What is that? In simplifying the luminance equation in 56. Oh, in the simplified luminance equation. So what's 55? Oh, okay, even simpler. So that's the BRDF plus the luminance. Okay. The illuminance of the light source for a surface perpendicular is said to said light source. Okay. Okay. So, oh, I see. So this is just okay. Got it. Okay. So we are okay. So it's a good idea. It's a good idea to use lux units. Lux. This was like LX. Oops. Units for directional light. Directional lights. Because it's easy to get these values online yourself. But also simplifies the... Okay, this also simplifies the lighting equation. The light, sorry. This also simplifies the luminance. The equation described in oh, I didn't write that on the equation. Whoops. Let me grab that. Grab that guy. Not that it's like that important, but anyway. Okay. Cool, cool, cool. And we have this guy. Okay, so I do remember this in vector, when you're learning vectors, and you have to do a projection, and you get like a orthogonal vector to whatever vector you've got. Then you represent that with a upside down thingy, whatever that is. Yes, that's the official math word, by the way. Upside down thingy. Oh, let's grab this whole. No. What is this? Hang on, let me try again. It's the official nomenclature. Yeah, I didn't copy the whole thing. That would be the simplified. There we go. So I'm just going to fix this. C dot L N. Okay, in the simplified illumines equation of 56, N, I'm going to say E bottom or E orthogonal is, okay, so in this simplified equation, E, what is this? This fella? Is illuminated, has illuminated, is the, hang on, let me actually make sense of this English. In this simplification, the is the, right, there we go, luminance of the light source for a surface. Oh, this is such a good song. It makes me want to play all the Souls games when I listen to this, but I can't, because I would need to practice, and that means this game would, this game I'm trying to make would get delayed, and the dilemma of being a game dev. You love games so much you want to make them, but now you don't have as much time to play them. Ah well, it's the price I'm willing to pay, I guess, for creative output. God damn though, I do miss out. If the directional light source simulates the sun, the orthogonal is the illuminance of the sun. Okay, so this is simulating the sun. E underscore bot. Is it bottom or bot? Yeah. Is the illuminance of the sun, oops, for the surface perpendicular to the sun. Maybe I should just man up and play a Souls game and just be okay with making basically no progress every day, because I only get to play it like for half an hour at the end of the day or something. Anyway, Table 12 provides useful reference values for the sun and sky. Illuminance measured on a clear day in March in California. I see. So these, is that useful? Okay. Okay, so here is this is here for reference. This table displays things in luminant in what is it? It's yeah, illuminance. Light units. LX. For a clear day in March in California. Hotel California style. Alright. So although this won't be useful for what I'm making, it'll be a nice reference, I guess. Okay, so so the BRDF, I think I have this already. I kind of copied this out too early, so I'm going to add this table in and worry about that later. So 10 AM. And then 2 more. 12 PM. And then 5:30. Yeah. Alright, so I'm just gonna do these first because it's kind of straightforward. Oops. And then we'll worry about the others later. Sorry, the other bits. So 2000. So I wonder how they get the measurements for the sky just being lit and not the sun. Like, how do you know the difference, right? The sun's out there. So 150, comma 00, 81, comma 00. Alright, so the reason I wanted to do that then is because I want to just copy these out because it's going to be way faster. Oops, it would be faster if I had the latex symbols. Yeah, so this probably won't be that useful for us, but at least have a reference, right? So I'm just gonna do that, and then we just need sky, which is this, and we needed sun, sky and sun. Okay, fantastic. Okay, so the directional lights. Dynamic directional lights are particularly, this is like very cheap, are very cheap to, I say particularly because it's more precise, particularly cheap, whoops, cheap, to evaluate. To run at runtime. Okay, so let's just have a look here. I hope it explains a little bit more because the problem with my direct light, like you saw, is some of the things are facing the wrong way and it's hard to figure out why. So, oh my goodness, L equals normalized and float NOL is, yeah, let's no, I don't like copying and pasting code for just making sure I get it under my fingers, if that makes sense. This is the saturate function written out more explicitly for the HLSL programmers out there. So if you're doing that, there you go. Light intensity times n.l. So my problem, I think, is the normals of the model, right? What I mean by that is I'm getting maybe it's a bit crazy if I do this. Hang on, let me just try something real quick, and I've been writing that out. I'm kind of tempted to just have a value of n, like let's just try like a normal vector. Normal light equals vec3. I think this is normalized, but I'll make sure it's normalized for sure. 1.0, 1.f even, 0.f, 0.f, comma. Right, so I take the normal direction. And what I'm going to do is kind of do this equals normalize with a z. And now calculate the vec3 lighting direction, right? Which is in our case n.l, right? But we're not going to use we're going to use this. This is kind of nuts. I don't know if this is going to work. And then we're going to multiply that here, right? Like, what the hell does that do? If we truly... Ooh. Oh, my bad. I didn't see that. I'm blind to that one. Okay, so 272... Oh, it's a float. Yeah, of course, it's a okay, that was kind of dumb. It's a dot product. I'm trying to say it's a vector. So I'm kind of curious, like, what the heck is that's done? Okay, so it looks to me that we have no lights at all. Let me just try another value. I'm kind of curious. 1. Right, so let me take that out of there briefly. No lights. This means there's no lights. Never mind. I just wanted to see if I could get away with doing what I was doing. Yeah, that was not successful. Because my pain point right now, when it comes to this kind of... Where is the... Oh, yeah, there it is. Lighting direction. Let's get rid of this. No. Go back. I'm just going to press Control Z. Oops. So yeah, n.l. Okay, there we go. And if you look at the code that we've typed up, yeah, so illuminance, light intensity. I'm going to multiply that by the BRDF, which we kind of do. Oh. Final color is undefined. This would just be this. I don't know why that moves the dock. Anyway, oh yeah, we've got the slightly because what I want really is this effect, right? So they're rotated. Let me think about this. So we have the... Oh, excuse me. I need to stop staying up so late. Why have we decoded twice? Oh, okay. It's that. Where E, whatever E is, which is just a texture, decoded to high dynamic range. So we can treat it as an input. And what are we doing? So let me think about this problem. So we have a vector that points in a particular direction. And that is, the dot product between that two is it's the normal, I think, that needs to change relative to the direction, but I could be wrong. Let's look at Learn OpenGL for a minute. Still a good resource to this day, despite what some people say. What I'm going to look at is lighting, color, basics, materials, lighting maps. Where is this? I want a directional light. The only downside of this is it doesn't really go into details on... Okay, so let's look. So what is this for? Is it, what type of light is it? Diffuse, specular. Oh, never mind. It does something. No, I think this is the older. I don't think people use this model. Yeah, people don't use this model type anymore. So basic lighting. We have ambient. Just ambient strength times by light color. Yep. So what I'm looking for here is the directional light code, perhaps, something like that. Oh, excuse me. Okay, so let's read this real quick. So one last thing. In the previous section, we passed normal vectors directly to the vertex shader, to the fragment shader. However, calculations in the fragment shader are done in world space, so shouldn't we transform the vectors into world space as well? Basically, yes. It is not as simple as just running running them through simply multiplying a model matrix. First of all, normal vectors are only direction vectors and do not represent anything specific position in space. Second, normal vectors do not have homogeneous coordinates. I'm not sure if mine does actually. This means that the translation would not have any effect on the normal vectors. If we want to multiply a normal vector with a matrix, we want to fully remove the translation part. We want to remove the translation part. Okay. Note that we could write the W component of a normal vector as 0 and multiply it by a 4x matrix. Second, if the model matrix would perform a uniform scale on the vertices, we could change it in such a way that normal vector is not perpendicular to the surface anymore. The following image shows such effect of the model matrix, so yes, makes sense. Whenever we apply a non-uniform scale, uniform scale only changes normal magnitude. Its direction is not easily fixed by normalizing it. Normal vectors are not perpendicular. Normal vectors are not perpendicular to corresponding surfaces anymore, which distorts the lighting. The trick of fixing the behavior is to use different model matrices for tailoring vectors. This is called the normal matrix. Okay. You can use few linear algebraic operations to remove the effects of wrongly scaled vectors, normal vectors. If you want to know how the normal vector is calculated, we suggest this article. The normal vector is defined as a transpose of the inverse of the 3x part of the model matrix. Okay. If you don't really understand what that means, don't worry. We haven't discussed the inverse transpose matrices yet. Note that most resources define normal vectors as derived from the model view matrix. But since we are working in world space and not in view space, we will derive it from the model matrix. Okay. In the vertex shader, we can generate a normal matrix by using the inverse transpose function in the vertex shader. That works on any matrix type. Note that we can cast the 3x matrix to assure it loses its translation properties, and that it can multiply a 3x vector. Okay, so do we do this? Okay, inversing a matrix is a costly operation for shaders, so whenever possible try to avoid doing inverse operations, since so for learning purpose it is fine for an efficient application, you want to calculate the normal matrix on the CPU and send it to the shader via a uniform, therefore drawing just like a model matrix. In the diffuse light section, lighting was fine because we didn't do anything. We didn't do any scaling on the object. So there was not really a need to use a normal matrix. We could have multiplied normals with a normal matrix if... Okay, so let's just look at our normal matrix then. Has that told us anything new? So N... Yeah, that's the normal matrix right there. I mean, we could do it, but I feel like if we sent up a the way it described, which I don't think we do at all. Oh no, we do. We just multiply it by the inverse model matrix, which we've worked out. So that's our normal matrix. So yeah, we're doing everything right. Crazy, crazy. Alright, so what do we need to do? Alright, so we need to work out... I really want to work out this problem because I don't really quite get it. Let me finish off writing what I was doing anyway, so we can have this code in our notes. So right, so illuminance. And I've already written that, sorry. Apologies. Vec3 luminance equals. So I'm going to write my version because I haven't written it exactly the same. So the TBN matrix is not the normal matrix. I thought it was briefly. Out of confusion. Right, so I'm just going to grab this. And I'll kind of know a little bit better if I do this, you see. Oh, excuse me. Okay, so we get the normal of objects, and so the series of dielectric materials of various roughness under a directional light. Okay, so what we need to do is I need to debug this. This is one of the things that's like really breaks everything. The problem is right now is we have this issue, right, where, like I said, we have this base color. No, sorry, we have this if I go to these rocks, right, I really want to sort this out where the when do we work this out? I've got to think about this a bit. I wonder if the inverse model, hang on. The inverse model, so the normal matrix might not be updated with the model matrix? Let me check that out, because that could be it, right? Our normal matrix isn't updated with our model matrix. Therefore, we end up with this bad situation. No, this is correct. Yeah, go down now. Like, let's see. So our inverse matrix, which is, let's scroll down to our scene code. When we draw, we have to upload the data, and we are in here with, okay, so there is our model matrix. And where is this? This is already updated, I guess. So the model matrix would be, it should have been made up in here, right? When we do stuff in the, what is it called? When we do stuff in the dealing with, okay, so it's above this because that's the materials. No, oh, never mind, wrong way around. Materials is first, then the vertices, and so mesh draw. As far as I can tell, takes in a matrix here. And this is good because we don't want to do the inverse model matrix calculation every single time we go through this for loop because it's very nested. We do it in the draws when we need it. The problem is, oh, I don't know. Let's break this code right open, right? Let's get rid of the let's get rid of this and just see how this responds, because I'm kind of curious, right? Like, if I break the normals, like how are you dealing with that? Interestingly, the lighting is a lot less. I just don't understand, like, why in this group here do we have more lit? Which almost suggests that there's like a point light there, so I don't know. It did. That might be just for scaling. Sorry, not scaling. If you scale something, then it does that, right? The because this is the thing, directional light should light things up uniformly. I wonder, okay, here's the next thing. Is the model, hang on, does the model data even have the rotated data? I don't think it might not. Now, let me just talk through what I mean. So the model data is something that's like the final matrix or whatever. But what I think might be happening, which I could be completely wrong here, is that our model is not correctly transformed by the given physics engine. The physics engine does something to the object. We update that via its positional update. And what we might need to do is, okay, so let's try and hack this together in the vertex shader, which is kind of going to be the easiest, I think. So we have access to the model's position, right? Times model. So if I take these two together, we'll have the model matrix with the positional component added. And then we can build the normal matrix up from here, maybe? Map 4. So this is a hack. Don't do this in real life. So this is the pre-normal matrix, I guess. Then we go and, yeah, I'm going to steal the code from OpenGL, the goat, the OpenGL, because what I want is this specific bit here. Again, don't do this. This is not good. So this is what I'm thinking, right? We've got not enough data in this. So pre-normal matrix is now a normal matrix. Mat 3. Normal matrix. So this is going to tank the frame rate a little bit, but I don't think it's going to be so slow it's going to be laggy. But I think that's going to be correct, because I don't think it has the correct normal data. Yes. Okay, that was correct. Ah, finally, I figured it out. Holy moly, that was a pain in the neck. Okay, so now I've got to make this work. So let me show you what I mean. So we have one directional light that goes in this direction. Our normal matrix doesn't transform the normals properly because it doesn't account for the rotation. The rotation happens with these two multiplications together, which is kind of tricky because we don't want to do this on the matrix, on the you're saying don't copy and paste code to the community who doesn't actually see. You're saying don't copy and paste code to a community who doesn't actually see the code. What do you mean? Oh, right. Do you mean like I flashed that up and it disappeared instantly and you didn't see what I did? Okay, so we've got to get a correct normal matrix, which we can do on the vertex. Okay, so let's bring this back, right? So I at least know what the problem is. Thank goodness for that. Holy moly. They use AI to generate code. Fair enough. I see what you're saying. That's funny, that. Yeah, that is funny. Oh my. Oh, I'm so happy I figured this out. Almost. I know how to fix it. Our normal matrix has been wrong this entire time, so our directional light has always been wrong. I've been blaming stuff in the fragment shader, thinking that I need to rotate the directional light vector for every single rotated object, but my normals on the model have changed and they haven't been updated in this model because the physics engines rotated things, right? And the model matrix that we've got out needs to be rotated in the same way. So then we can get the inverse model, which means when we're not doing a transpose inverse on the vertex shader, every single vertex. So now I got to figure out how to do that. I kind of know it. I've just got to be careful here. This isn't going to be too bad if I can get this to work. So that's very, very satisfying that I can get this to work now, because my goodness, this has been confusing. I can't believe I accidentally found the right thing to look up just by coincidence. Okay, so because the normals aren't facing the same, so because the normals change. So if I rotate the model, right, and the way we figure out what it should be looking at is the normal vectors of the surface. Now, if I have rotated the object, right, and I haven't updated the normal vector to normal matrix to reflect the transformation that the normals need to go through based on some change, then the normals of the normal calculation is going to be wrong. Should it be independent of the position of the object? No, because if you're rotating something in model space, that needs to be reflected in the normal matrix too. So the normals get updated when you translate or rotate a model. That's just how things work, because normals are a reflection on the surface. Okay, so we have to I have to figure this out. Give me a minute. So we do have the data here, but I need to get it out. That's the position. Into this. The problem is... oh, where am I? This is not the right thing. In this, right? Okay, this is going to be tricky, because I've got to have... This data's got to carry over. Unless... I make my life easier, and I store the model matrix and the inverse model matrix in the same thing. Right now they're in separate places. So if I store the rotation, the inverse model and which is the normal matrix, and the model matrix in the same place. Oh, that's tricky though. That's not going to work. It would be nice, but I would have to redesign this whole engine. Maybe it's appropriate, though. Okay, so this is what I'm thinking, right? Per instance, we have model data. We have positional data. And let me just talk through this, because I'm kind of like... We also have this, which is technically per instance, right? Let me just look through this. Instance of reflection, emission factor, different flags, occlusion, roughness, and all that kind of stuff. Despite it being accessed in a uniform buffer object, I'm starting to think, right, what happens if I stick it all in here? What happens if I just throw it all in here? And we just do a giant mem copy from one thing to another with our... Instead of having a descriptor set separate, we stick them all together. That means when we update the position... let me think about this again. That means when we have a position object... we could do the inverse transform on the CPU, update the inverse thingy here, and the rest could be mem copied. Right? That makes sense? It's a bit of a risk. This might not work at all. So the let me think about this. This is tricky. So if I have a... If this is all in one data structure, and it's updated in two different ways... I'm basically trying to combine buffers. And I don't know if it's a good idea yet. So I do a mem copy because this is a... I have here, this buffer here, right? You know what? How about this? How about this, guys? What do you think? What do you think? We just put the inverse matrix, the normal matrix, in here. We just put it in here. We don't complicate anything. And we just kind of go that way, right? So, I'll show you the mem copy, though, to answer your question. Make another cough. Same in the descriptor set. So this is descriptor set stuff that we're dealing with, but we're accessing them in slightly different ways. Anyway, if I go to my code, what I'm saying is instead of just doing a small amount of data in here, why don't, this is a mem copy, by the way. This is a VMA mem copy. It's a bit more, it's got a bit more involved to do this mem copy, but what I was saying earlier is, instead of having position, debug, model, and which is used for something else, and color, we just throw literally everything in, right? The color, honestly, was just to test things. But what we could do is, if we had, we need access to the, we need this. Okay, this is not a good position. Let me think about this. This is going to be a bit of a rewrite if I do this, even if in the simplest case. But it might simplify things. To transform model, to transform the model normals to world space, we just need to use the model matrix like this. Hang on, give me a second. Are we in world space there? World matrix, matrix, normal XYZ. Kind of. No, I think you need to do an inverse. I'm confused with that, honestly. World normal equals matrix times by. Okay, so that's true, I think. Right, let me look through this code again. So Mohammed, we need to get that matrix. You see that matrix that says model, the model world matrix, the mat? That needs to be the inverse of the model matrix. That's the problem right now. I need to be able to communicate this inverse model matrix to do to move models into world space like you said. But I need to be able to combine the matrix. Sorry, I need to be able to combine the model matrix. Unfortunately, is in a completely different buffer to the position data. And I need both to combine them into a inverse model to get the inverse model matrix, which is correct. Because right now the model matrix is separate, unfortunately, from the positional data, which is fine. But because I multiply them on the shader. But to do an inverse transpose on the shader is expensive. It just doesn't scale very well. It's not like it's going to slow my game engine down very much. It probably won't be noticeable. But let's just say I have 40,000. No, let's just say I have 400,000 models on the screen, and each of them has like what? At least 1,000 vertices, right? We have like an insane amount of this inverse transpose thing. The inverse is the actual issue, not the transpose. I am aware. So I need to find a way to basically either get this positional data to here, or get the model data from here to here. And I think it's going to be easier to get the positional data, store it, multiply it by... no, it's still not going to work. Because these are effectively different for loops. They are very different deliberately. This one's looping through all the entities. This is looping through all the models, and then all the sub... Okay, this is tricky. all the submodels inside that model. Sorry, so I should say meshes. This is more meshes than models. Than ignore the. There should be mesh type. No. These are the models, and these are the sub-meshes. Okay, not mesh index. That should be sub-mesh. Within a model. Because sometimes you need different materials for a given model. And so you can't just draw it in the same way. Okay, so... Oh, I'm getting further away from the mic. What I think is going to be the easiest thing to do is getting the position somehow for a given this guy. Oh, because they're so disjointed right now, this is kind of tricky. Oh, man. Yeah, because it's a completely different paradigm. Okay. Because these buffers are handled completely differently. So they're updated and created at different places. Alright, this is tricky to figure out. So, models. We have models. In one buffer. And we have the position in another. They need to be combined. To avoid doing this inverse thingy. Now, all I need to know is what position corresponds to what thing. I don't think there's a relationship there, but let me think about this. Is this making sense, guys? Let me know if it isn't, and I can explain it better. So I just need this position data to be tied to this model data. That's what I'm trying to connect. I'm trying to connect the dots here. Because what I could do is just like, you know, X. Well, it'll be here, wouldn't it? X position, right? That's what I'm trying to think of. Like, how do I get the... What model corresponds to what position? Is what I'm trying to figure out now. Because yes, I could just send in this here and just multiply it by the model. But if I just say, if I don't get this right, we're going to end up in a situation where the data I'm sending over is not going to be any good. And that's kind of tricky. So that's the idea anyway. If I can get this multiplication to work, then everything works out. Our lighting normals are working. So this is never going to work. Okay, just so everyone's aware, like this is the reason the point light never worked. Okay, everything's making sense now. Everything's making sense. The point light was broken for this reason as well. I never understood it because it was really strange. Okay, so everything's made sense now. Why I was struggling with lighting so much was this particular issue. My normals went in correct world space. Now I just got to figure out how to get him out. It's not, unfortunately, easy. As far as I can see anyway. I can't see an obvious solution. Because this is the thing here. This is the issue. Well, sorry, the communication between these two is just not the same. The reason is because I want to... There's way less for loops here. Like, the density of for loops is like... There's only like 3 elements in this at the moment, and there's only... depends on the model, right? So, these are a bit disjointed. And based on that... I don't know how to get that position, because this is for every entity. So, for example... Should we just try the most naive approach, guys, and just see what happens? So what I'm thinking the most naive approach is to store the model matrix. Kind of like... let me think. So effectively I index into this buffer, which I don't want to do, but no, sorry, I index into I do this, right? I do this. This is what I want to do. And yeah, this is slow as well. Ugh. I want to avoid this as much as I can because this really slows things down. Get world transform. Ugh. Dang it! This is so tricky. Okay, so let's think about this in a different way. We can do. Let's go up a level. Instead of doing it at draw time, let's try and do it at initialization time. So we have the transforms here. Sorry, the rotation. No, we would still need to do it at draw time. Okay, so let's just get this sorted with, because oh, this is so tricky. Which is better? Which is better? How do I do this? Okay. Okay, I might be... Okay, because I've got to do this draw time. I'm thinking, instead of trying to multiply the thing down here, I do the opposite. I have more details, right? I have model is equal to that times model, right? Okay, let's try it this way around, because this might be easier. So now I've got to pull out the mesh draw data. That is by... do I have this data in model? So what's an entity again? So model type, I think I do. I have the first bit. So if I get to... This actually might be doable. So if I get scenes model that, and I get the entity model type, which is this. So let's grab everything related to this. Okay, so I'm so excited to fix this. This has been doing my head in for ages. I can't believe it. If I could just solve this, like everything would work. So model type. So we can get at least this far. That isn't enough though. We need to get to model like mesh index. Now, I'm going to take a super naive approach here because this for loop. What we could do is increment a number by 1 if the mesh type is equal to that type. So what I'm thinking here is very crude. So we have... This for loop is doing one thing. It's saying, okay, get the size in this, right, and increase the number by 1 starting at 0. If this is true, which is the model index, which is what I could count. So let's just say uint32 model index, or like, not model index, not mesh index. I don't know. What's it called? This model index for position. Let's say position model index. How about that? Position model index. It's not quite right, but I can't think of anything immediately. So this comes here. This goes in there like that. Oops. So if this is less than that, then we increase this by 1. Okay, so this does it for one type, right? So I put this in here, and then I say dot mesh draw. That, right? That's the tricky part. This multiplication can be fixed. Because Because then I can get the model out. Oops. Then I can get the actual model out, right? And multiply everything together, right? By this thing. That would give me the official final model that I actually need to be working with. And I could also do the inverse here as well, shortly, which I could do. So I probably need to do the inverse. The downside of this approach is it's only true for a... This would need to be incremented per model type. So if you notice that this is like a... This is only going to work for one model type. What I need to be able to do is basically have a number that increments by 1 to access individual elements of this array as we go through each model type. So that's kind of annoying because I need like multiple numbers that just increment by 1 based on the mesh type, on the model type. Okay, so the thing immediately comes to mind is a switch statement that increments by 1 and that has like 5, 7, 8, 9 variables or whatever is required. But I feel like that's kind of clumsy, and I would like to be able to find another way of doing it. Just thinking about it. So I need to go in here per model type, and the reason that this needs to be done, by the way, at draw time, unfortunately, is because if I interact with the model in the physics engine and then change it, then that needs to be updated, right? Ideally, you would have a system where it does this initially, and then only when you've interacted with a system, then it updates the model matrix. But this is just simpler for now because I don't want to have to deal with 2 cases. I want to just deal with 1. I can deal with that afterwards. So multiply these together, but I need this to be incremented by 1 each time this is found. Is there a good way of doing this without just having a bunch of variables? Because I don't want to have like thousands of variables just to index into a bloody array, you know? Per model type. I literally can't think. You know what? Let's do the simplest. No, let's do this is only going to happen for dynamic objects anyway, so what I'm going to do is, you know what? No, I'm going to comment this out for a minute. And do this. Comment this out. It's fine for now. It's kind of like a to-do to myself. What I need to do is I'm going to do this on initialization because that is going to be a niche case. That's not going to happen for every single thing anyway. I've already got that set up where we only update things that have been collided with, based on dynamic, based on a dynamic system. So, all right, let me think. Let's play some more. Do you guys mind me listening to that again? I kind of enjoyed that. Okay, so we have a model created here. Let's see if I can get this done earlier. So this is done first. This is 100% done first. We create all the buffers and stuff first. And I wonder if it's possible. It's only the rotation really that I really care about. I don't think the translation changes anything. So that's us working out the model matrix really. Here. This needs to be multiplied by the position that we care about per instance. Because if we're doing instance rendering, this gets tricky. There's not a draw call per instant per object drawn, because that would be expensive. Man, if I could only do this on the shader, this would be so trivial. It's almost like I need a second buffer device address accessed buffer or something. Another VK buffer to rule them all. How about we take... I got an idea. I think this might work as well. This might do it. So what I'm thinking, instead of doing all this, we at every loop we create a new model times by its position, and then we just send it into here. We don't have to access it. No, it still doesn't quite work. Because what I was thinking is, because we still need to access the model. And that just brings us back to this situation again. But it does make sense if we pull it out, because it doesn't work here, I don't think. But we need to read from a buffer, and I don't want to read from a buffer. Oh my goodness, this is complicated. Okay, let's try again. Physics engines broken my... The physics engine's broken my normal vector, normal matrix. And it's so easy to fix in the shader. Because we have all the data there, but it's not... I need to combine it in one of the buffers before that point, and that's the tricky part. Oh, my goodness. I'm so glad I found it though. This is the issue of the week, if I can solve this. Because it has broken so many things. Yeah, so to get the position in here, that would be per instance, that's the problem. And we would need to read from a buffer anyway, which we don't want to do. What we can do is read from mesh draw. And we establish how to do that here, I believe. This thing, we could just do convoluted double access of an array of arrays. We can get this far very easily, but we can't get this far very easily unless we store extra data in the model. I don't think there's any way to get to here without any without anything that's kind of useful per model index. Because if we store what instance we're on when we're uploading things in mesh draw, sorry about making that noise. So if I take so this is again demo code. This would need to be moved. This can't be in here. This would need to be done every frame. Sorry, for every instance. So this would need to be moved down here. Well, maybe I could get away with it, but like once it happens and then the rest it doesn't. Hello there. There is a staged alien invasion known as Project Bluebeam coming soon. This will be done to explain away the rapture of Christian Church. Okay, sounds good. I will be aware of that. Thank you. But we don't want to talk about religion here. This isn't the stream for religion. Hopefully you can appreciate that. Anyway, so let's figure this out. We need to do positional less than maybe we could do this like once per frame and not do it multiple times a frame. That might help. I don't know how expensive this is. And then only update it every frame here if we need to, based on rotation and translation changes. Okay. Cool. See you, dude. Thank you for joining the live stream. Okay. We got this, guys. We got this. This is just a few errors away of working out. So what I'm thinking is, if I go to models, what I'm thinking of doing is having an extra variable in here. Instance count. That might be what we need. Is the instance count... we kind of like it. We need to like recount the instance count. Almost. Because that's what we need to do. We need to access per instance. Oh my goodness. All right, let's just do this dead simple, right? Let's do this simple. It's gonna be straightforward and model, current model or something. Used to access / keep track of model matrix per instance, which is done at draw time. Okay, so we need to think about this one more time. We have a value that we're going to increment by 1, and this incremental value will increase each time we access this model. And we're just going to do this manually for now, but we can probably do it maybe a different way, I don't know. And this will be counting the instances up so we can make sure that... Because what I don't... I wanna. This is the problem. This is the problem. The rest is simple. If I could just solve this one. So. If I have a vector. It might be worth putting this into a... Yeah, what I'm going to do is just for faster turnaround to test things with, I'm just going to make a demo program real quick. You've seen me use this before. This is a good technique for debugging if you've never... Oops. If you've never done it before, that's not the project I care about. I call it nebula because it's like vague. Yeah, we don't enjoy physics. Alright. So, I don't know what was this... Oh yeah, so we're gonna rewrite some of that, but I kind of want to make this simple. And we have a struct, and this is the entity data, which is just going to have a int for position. Right, and we have a struct called model, which has a uint32 model. Yep. And then we have a struct entity, which needs an entity index. And we want an enum. Model type. Right. So, duck, rock, yep, etc. Okay, so these are two buffers. These are two buffers. Then we need model type. Oops, come on. Model type. Model type equals. I'll just put count. Just my own insanity count. Okay, so this is equal to uint32 max, and let us build this up. So this is our system currently. We have oops, int main return 0. Okay, so we have a vector of models. And I think... Oh, yeah, I also need to have mesh draw, which is a model within there. Hang on, let me look at my code again. My actual code. So models has... Does it have a struct in it, or no? It has another array in it. Okay. Struct mesh draw. Okay, so that's actually the thing. If that's where actually it is. Why is it... Hang on. Okay, I'll come back to that. Okay, so this is the model. And this is standard vector, mesh draw. Mesh draw. Okay. Okay, so when we create mesh draw, we go model. This is the create code. And we go models, mesh draw, at 0. push back. No, this will be push back a position of 1 or something, 10. And this happens when we create an entity. In the entity, sorry, entity. It's a vector of entities. Entities. So we create entities, right? And we go push back. Oops, wrong. So this would be 0, right? Then we use that. No, it needs entity index dot entity index equals. I'm just gonna put 0 for there and dot model type equals. We'll do duck for now. Okay, and okay, so that's the first entity, right? The entity index that we pull out of there, so the uint32 index, I'm just going to call it. We don't have stable IDs yet, so just bear with me for this one. Entity index. This goes into here. No, and we just need model type. This song is so good. Model type, and this would be not that, this would be model type. Okay, so based on model type, we index into that, we push back 10. Fantastic. That's the model. That's like the actual. This is a stand-in for the actual model. And so every time we create, let's see if we can do this in a for loop. We need to pull these out because these are going to be separate. Okay. uint32 I is equal to 0. I is less than I don't know 10. I should do 1 for now because otherwise I might get trapped. Okay, so I. Right, next is the next vector that we need to worry about, which is the standard vector of entity data, which is different again. So we have, the problem here is we have we're accessing things at different times. And this would be, do we access by ear? How do we access this? Sorry. I think this is literally just in a straight list from start to finish. So dot pushback. Also, we would need to push back our models. Otherwise, we wouldn't have anything to push to access on. So pushback, or create. And here we would need to add a. Yeah. Okay. So this is actually. So dot mesh draw. Can I do this? I don't even know. Can I push back twice like this? I have no idea. No, you can't do this. Right, I'm going to type it all out and just see what happens. I don't know how much I can abuse the C++ standard here. Okay, no. Okay, so what we're going to do is create a simple struct. Then we're going to do that with it. You're going to be able to access it based on. Then we can push back, and we can in position. So this would just be, I don't know, 10. Oh, yeah, it would be a struct with 10, sorry. Dot position equals 10. What I might do is, if I ever do a for loop, I'll just times it by I. So it's always changing. We have an R value. I think we can just do R values. Okay, so the problem is I want to be able to display, well, in this case, hand over to a shader. Oh, we don't have standard out. Okay, so let's do printf. I feel like I've been writing standard out for no reason. Standard IO.h, right? Or C standard IO. Okay, so printf. And we want to display model plus position. And this is the tricky. How do we match this data with this model? Because if we run this, let's just assume this works for a minute. Like a lot. And the model types I make are, I'm going to pretend this is random, right? So let's say model type type is equal to if modular 2 is equal to 0, then we're going to do duck. Oh, question mark, I always forget. Oh, yep. Else rock, right? And we're going to put type in here. And we're going to make the entity index I. So that should work. That should build a list of entities that have indexes that index into model and then data. Oh, man. Maybe I should have just used ent. I talk about being simple, and here I am making a fucking super convoluted thing. Oh dear. Oh dear. How do I know which model type to access when I do this? Models. So the question of the question is model type. Model type equals I think it's fine. So for, and the loop I'm trying to go through is the entity loop. So uint. Oh, I can't be bothered. I'm just going to write an an enhanced for loop because I can't be bothered trying to figure out the minutia. So this is the draw loop. This is the no. So I'm going to write a setup and update / draw. I don't even know. So this has model type equals entity dot model type. And this goes in here, very nice. This is actually quite straightforward. Very good, oops. Next is the data. That is accessed by so add these together. Data is okay, so entity, this is uint32, entity index equals entity dot entity index. Fantastic. Right, not done yet. Dot mesh draw. It's thrown a random number that should start resolving. No. Let's just check something. Oh, the addition didn't work. Oh, that's why. Right, that should get rid of this. Dot position. Okay, so that should work. Okay, that should compile. But the question is, how do I get this 0 out? Oh, comma. %d. All right. So new line. Question: I do not know this bit of the equation, and I don't know how to keep track of this. Like what type belongs to what mesh draw? As I loop through each entity. I'm gonna go to the loop. But that's the problem. Hopefully it's a little clear. If it's not, I apologize. I know this is a bit convoluted, this type of entity handling stuff, but the general principle is we need to be able to combine two things from two different buffers, and that is currently not working for us. So yeah, we're in a bit of a bind here, and the problem is the second array. The first array I can always access. The data I can always access easily when I loop through the entities. But when I try and get the mesh draw that corresponds to the arbitrary point at which this is in. So this could have one mesh draw in, it could have 400 pair type, I don't know. So I'm gonna go to the loo and I'll be right back. Alright. And we'll keep attacking this. But this is going to solve like so many issues in the engine. It's so important to solve. It's a really big issue, this. Now I've found it. Now I can at least attack it. So yeah, I'm going to pause my. I'm going to move to dev. This is full on dev, and we're not studying anymore. This is more important than studying lighting, because this breaks everything. This breaks all lights if I don't get this right. Alright, see you in a minute. Alright guys, sorry I had to kill a fly while I was away. I saw red. Had to do it. I committed fly-aside. Anyway. Let's see. Okay, so I unfortunately didn't get a lightning bolt from the deep to tell me how to do this. But generally what I was thinking is I'm storing extra data in here that keeps track of something that we can increment by 1 every time we access the model type. So this is what I was thinking, right? uint 32 counter. I don't really know what to call it, but I'll just call it counter for now. This is always equal to 0. And this is just based on the loop plus... No. Every time we do this, which I'm just going to kind of store the model. No, we get... Sorry, we do this, we get counter out. Oh, let me start the music again. So we're on full-on dev mode now. We're not doing any studying. Mesh draw. I have to admit what we end up working on is very up in the moment. So anyway, so no, it's counter. Sorry, counter. Come on, where's the mesh draw? Oh, I put it in the wrong thing. Yes, I did. It needs to be in model, not there. So it's like, okay, every time we do something, get rid of this. Counter, right, is equal to this. So you gotta remember it's pair model type, which is different. Because the model type is going to be different every single time. So it's not like we're just incrementing through a for loop. Model, sorry, counter or whatever. It's equal to this. And as soon as we've done that, we kind of need to add. So maybe I should make a function, actually, instead. So what I'm going to do is make a function. A very simple function, but it's going to hopefully encapsulate this behavior. Void counter. And based on that, it's going to return... Oh no, it needs to return a type here. Okay, so it's going to return a... It's going to return a counter. No, it's going to do a uint 32 counter count or current count equal to counter, and then counter plus plus, and then return current counter, right? So you could probably call this something else, but that's like 2 things in one, so it's going to be easier to handle. That means we just need to do this instead, which is kind of easier to handle. And that then is going to tell us what model type plus the position, right? That's the tricky part. Because the position needs to correspond with the data index plus the type plus whatever type are on the instant type. So this would be instance counter, I guess. So let's see. So we're probably going to get assert here or something. Oh, let's see, instance counter, redefinition. All right. Yeah. So that worked. And I can probably print out the model type as well. It's still not my favorite approach. I don't really like it that much, but it's better than nothing. So current model type. So let's say if model type, do Control S here. If type is equal to duck, then we say duck, else, oops, rock. Hopefully that can be evaluated. If not, alright, so the duck and the position are these added together. The rock is added these, this. You see what I mean? Like, if we just went through a for loop raw, we would be like duck, 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 and then rock, 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 which is not correct. Because this could be in any order per instance. But I think that's such a... Why can't everything be easy? Anyway. Right, okay, so that's as far as that's as best I can do. It still feels clumsy, but that's the only way I know how to track where we're up to on a given array within an array. All right, let's write it. I'm satisfied. So instance counter. And we need a function called uint32 instance counter. So we just need to do exactly what we did earlier. I'm almost tempted to throw it in here, but because it's const, I should put that there, I guess. Oh no, it modifies the state of the object. It's not const, literally by definition. But I think this will make this easier to deal with rather than indexing a bunch of weird stuff on the fly due to the data being public. I think this is going to be easier. Okay, so return. Okay, so uint32. Actually, let's do this first. Current count equals, and then return current count. Did I say void? I don't believe it. If not, I'm going to see the error. Alright, let's get rid of this just to see the error. Don't need any more errors. Oh, I see. Right, it's the same thing as before. Say value. Fine. Array instance count. Right, okay. Literally made that mistake just before. Okay. Now, when we go into main, we can pull out the data that we need per object, per mesh draw, wherever the game is. Okay, so now we are in here. Right, I'm going to do this here for now. So, model type. I see you met G. Oh, yeah. Let's not talk about religion. I don't know if that was a joke, but yeah, it's not really the place. All right, so what we need to do is get the instance counter. Put this in here. I don't know what to call this. Current access dot instance counter. Okay, so if we take scene, instance count, access that. Why are you complaining? Expression preceding parentheses must. Oh. There we go. Now when I do this, so this is step 1. Done. That is good. That helps out a ton. It might even make sense not even to do it like this. I have a thought that I can make this even better. No, it needs to be... Oh, we can't take out... No, we need to do it. What I was thinking of is maybe we can multiply the model and the... The thing is we can't read this value. We're not allowed to read to it. And if I passed it in as an argument, that's reading. Or is it? If I had a pointer to it, is that still reading the value? I'm not going to risk it. Okay, so now we need to do the next step, which is... I'll copy that off in a minute. Getting the... Oh, we need to do every single frame. Oh, it sucks. That's going to slow everything down by quite a bit. Okay, so I'm only going to do this for updated models. It's just too slow otherwise. I'm going to have to find another way of doing this. I literally cannot afford to do it like that. What is this? This is a mat falls. Okay, so we can at least do it for models that are being updated. Okay, I just can't do it per for every single frame. This is going to take way too much time, but that's fine for now. So instead of doing this conversion twice, I'm just going to do it once, which is fine. So model, so it's map falls, isn't it? Map falls, model position equals this, because this is not free. This needs to be above this. That was not quite right. And this here. Now this, oops. GLMs. Mul. Okay, so we can at least get this far. Which is a step in the right direction. And also this needs to happen here. Not ideal, but okay, so we've done that. So that's the next step. Okay. Oops. What am I doing? I was here for a reason. To avoid this double conversion for no reason. Boop. Okay. Fantastic. Now we need to get rid of that red squiggly line and update that in the shader as well. Which means entity data needs a mat force model. Okay, and that should go away. And now we need this in the shader. Now this isn't going to fix anything, but it's a step in the right direction. Fixing this horrible issue. So I need to find. Now I'm gonna have to use this, which is fine. I know we're not. It's only. I think it's only the vertex shader. Mat for model. So every time you see this struct, we need to do the same thing. Oops, same thing. And let's go fixing one thing at a time. This needs to go here. Now I'm not sure how the padding is going to work, so we might have to readjust the padding. Oop, I said that's not right. I got mode every single time. I did. How annoying. Okay, scroll down. It's just the padding in there. This. Hell. Are you doing this as a compute shader? No, I'm just... What I'm doing here is adding all my buffers. I'm adding some extra data to the buffers to have this in there as well. But I've got to... At this point in time, I've just got to make sure it works. So what I'm eventually going to end up doing, I think I'm going to remove this and add this into a material buffer, which has got all the materials in. Because right now we're losing track of our models based on. So we have a normal vector, right? A normal matrix, which updates the models, which updates the normals of the model. But that needs to be updated with the positional and rotational change of the model in model space. So at this point in time, we need to make sure that we at least are able to multiply the positional change per instance per model. Now you may think, well, aren't you already doing this, escape point? Like, literally. Like, if I scroll down here, you're like, bro, this is the whole point. You have global scale, you multiply the position by the model right there. Why are we doing it on the CPU now as well? Well, because what we're really trying to target is this. What we're really trying to get away with is this transpose inverse model matrix thing, which is expensive to do on the GPU apparently. Now, I don't know how true that is anymore, but I think I need to profile it, I guess. So what I'm going to do is do this super convoluted approach and then compare the frames. If this is faster, then I'm going to do it on the GPU. If it's faster on the CPU, then I'm going to do it on the CPU. But to do it on the CPU, I need to do a lot of work to get this to work, because there's two different buffers that contain two different things that are accessed at two different times. when I mean accessed is like the model. This guy gets accessed every instance. This guy, well, oh, never mind. Wrong shader. So this guy gets accessed every instance. This guy gets accessed every vertex. So there's an inherent difference here that's kind of hard to map. And what I'm trying to do is make sure that nothing corrupts. So let's just see what happens. Now we could get a bunch of flashing data. There's some padding in here. That's still a thing. Okay, yeah, we don't need that, but that's not going to affect anything. So, okay, so we end up outside the range. In the loop, yes. What's the model type? 0, 1. Alright, I'm just going to do this for now just to see how this works. So if it works. What I came up with does not work at all. Oh. Yeah, I put it in 2 different places. My bad. Okay, so we don't get anything corrupted. Now, if I take that model data that now we have in the shader and I use it, what's going to happen? Now, we know this works already, so what I'm going to do is this, get rid of this. What happens now? I don't know. Right, this, get rid of this. So this could completely break everything. I'm leaving the debug geometry around just for sanity. Yeah, okay. Weird that we only get, I think the rocks aren't updated. We get a giga flat duck. Oh wait, okay, hang on. It's just huge. I don't know why it's so big. What about the other ones? Do they exist in their original size or? No, they're not there. Oh, that may be that one. Hang on. No, I think they've all. No, this wouldn't work. If I can't get this to work, then. Oh, this is so tricky. You know what? I'm almost tempted not to try and do this, because it's gonna. Oh, this is gonna take so much work to rework. Well, it's. I don't know. It's just because this is so easy to fix in the shader. This is literally it. It's all I need to do. I can even add the point light back. Let's add the point light back, right? Because that was where is the point light? Oh, here it is. V.L, yeah. So there's the V. And then the L is the capital. This is the point light version. So this is the point light rather than the directional light. So we have all them. And then we need to actually use it. In the old fragment shader, I actually use it. So that's the intensity, that's the range. So I'm going to grab these two. Obviously get rid of this. And this. And call this dist because this is a and intensity is used when multiplying the color, which is just the same as our luminosity. Nope. Right, there we go. Error. Oh yeah, distance is now dist. Alright. There we go. You know, one thing I don't ever want to touch again is shader programming. I did a course about it, and it was pure pain, suffering with little reward. Ah, that sucks. Yeah, it's a tough one, I guess. I don't know. Maybe I'm a sadist and I kind of like it. That was a redefinition here. Let's get rid of this and this. Yeah, it is tough. Alright. Okay, I'm just going to ignore that. Do we get a point light? No, why are we getting no lighting at all? Oh, it's not following us, that's why. Sorry, there's a... I changed something, and our light is not being updated with our position, which is quite easy to fix. Because it's literally just this. Let's grab this from our diff. And then 1.f. I mean, there's a good chance it's just me being dumb. And I'm okay with that. Yeah, it's no, not that. No, it is hard. I'm not very good at it myself. There we go. Okay, fantastic. So we got the light kind of doing its thing. So it's kind of interesting. The metalness of this duck is kind of looks kind of funky with a point light. So yeah, feel free to don't take my word for it. I'm not an expert. Yeah, there we go. This is lit. This is more or less lit correctly with our current BRDF. We have some glazing angles that are kind of odd, but for the most part, when I get close to the object, it is worked out properly. Man, none is dull in graphics programming. Yeah, it's honestly graphics programming. Even if you're just doing the technical artist stuff in like some program, in some game engine, you increase the intensity of this. I don't know. Unreal Engine or something, or Unity. It's still tough. It's still honestly quite tough, and I've barely scratched the surface of like how deep it can go. So yeah, oops, nope, not what am I looking for? Oh yeah, I need to. Yeah, the I think I still need n.l. I came here because I'm relearning programming. There we go. So it wasn't quite right. No, it is. I came here to relate. I don't know. I don't know what. I don't know about them, but it looks good. Ah. Yeah, thank you. Thank you for saying it looks good. It's yeah, my ability when it comes to shader programming is definitely worse than it is my general programming ability. Okay, so my direction is wrong, but I think it's generally my normals are at least correct. And if we use directional light, let's just get rid of point light for a minute. That was a bit disappointing. If we use directional light, this kind of just works, and that means the point light should work fine if I code it correctly. Which is this, oops, and this, right? So if I code this correctly, we have a directional light that faces the right direction. Turn off that. Oh, the light is following me. Hang on. I'm doing n.l on a. So let's take L and make it lowercase because this is a different light. I'd love to apologize for that. That was not correct. I'm going to get rid of these for a minute because I'm not going to use them. So, directional light. What sort of game I'm making? I'm trying to make like a space game. I hope your learning progress goes well, by the way. So, I'm trying to simulate like a little like space lighting at the moment with like harsh directional light, right? If you imagine that sun over there is the sun, and yeah, that's what I'm trying to do at the moment. You're kind of like in deep space. You're gonna be floating around, doing stuff like that. Kind of like, I mean, it looks okay, but it's just the way I'm doing it. It's just not very efficient. It reminds me of with ducks, of course. Yeah, with ducks. It reminds me of EVE Online. It's looking good. I love space games. I appreciate that, dude. Yeah. I'm trying to make this as good as I can for people. It's going to be a bit arcadey. It's not going to be so serious. Hence the ducks. I mean, they're just there to test, but yeah, that's the vibe I'm going for. A bit arcadey, but I want to make the lighting nice. You know, it's really important to me that I get the lighting like good. Because I think graphics are the thing. The lighting is in my control. I can make the lighting really good. I can't necessarily do modeling. I can't do a lot of other things, but I can at least make it look like pretty if you take a screenshot with the lighting. So yeah, that's what I'm working on at the moment. Oh yeah, the 1.8 gig is it won't be that bad on modern hard on your computer. One, I'm reserving 1 gig of memory, and two, Visual Studios is increasing that by about 300 megabytes. I can reduce that memory quite a lot. I'm just having it there to mess around with, right? I'll figure out like how much RAM will I actually reserve, and then I'll reserve that amount of RAM, and then that will be what we end up using. But it still will be pretty big, but not nowhere near like a 1.8 gig. It's not going to be a Google Chrome app. Yeah. I don't want to be you people playing this game and then having to choose between Google Chrome and my game because they're both eating so much RAM. Considering the price of it, anyway. Is the skybox emitting light? Not yet, but that will be on the cards. But I'm still struggling with this issue. Yeah, it is. I've recently came into a brick wall. It's not because I don't know where to go. It's just that my laptop stopped working. Oh, that sucks. It keeps pressing 4 and I don't know. Oh, that sucks. That really is annoying. MC is. No, I really hope you figure that out because that is really irritating. You can't really do much typing if it's constantly printing 4, can you? Right. Okay. So. That would be us done if... Okay, so what I'm going to do is... I am going to break my model... So I'm going to compare frame rates. How bad is this, actually? Right, let's actually see. So I'm going to check... Inverse... No, it's model inverse, isn't it? Model, yeah, inver. Right, so this is what it used to be, and I'm gonna have to compile for release. So let's compile for release because I'm going to compare frame rates now. And to do that, I need to turn off all the logging and all the printing and all the error checking and stuff like that. So, oops. And we're just going to see how fast, how much performance hit this is. Because it says it's a performance hit, but this article was written a while ago. So I'm actually going to check how much performance hit this is. So we're going to disable this. Oh yeah. It's still pressing 4. Oh no. Yeah, if you could somehow disable your keyboard on your like disable it and maybe even unplug it inside your laptop. That might help if that is the issue, but just be aware you got to be careful with that one. Oh, I need to compile. What am I doing? I haven't even compiled yet. Build. You have to lobotomize it, yeah. Oh, I do need to copy over the new models and stuff. So while that's... Actually, I'll leave it till later. Right, okay, so that's compiled. Now let's copy over all our data that we have previously. Oops, that was actually where it needs to be. So I'm going to copy almost reflective metal duck. I think they're the 3 ones I care about. Into my release build folder, which is here. Model. Excuse the scruffiness, by the way. It is pretty shocking. So paste, and then we need to update the shaders because this is a shader check. Shaders. Yeah. So here, build, release, shaders. All right. Replace. Okay, so we should now be able to run our release build. Cool. All right. Let's boot up Intel on and attach it to our game engine. And what we're interested in is seeing the frame rate, which is okay. So it's settling around about 1,000. So I'm going to take a screenshot of that, of like something. Excuse me. And kind of see it's like new. Okay, so that's just going to make it go slow. So I'm just going to have to remember between 1,000 and 900. How about we have a generous range, right? And now I'm going to do a 1 millisecond. Nice. With it's increased in complexity, the game engine. There's a lot more going on now. That's why it's slowed down. But it used to be 2K, 2,000 frames per second. Now it's at 1,000, but that's a bit like a barely slowed down at all. Because frames per second is as the frames per second gets high, they're okay, so the only thing I'm going to change is this. So let's break into this. Tab. So apparently this is going to slow us down. Let's see how bad it does it. Yeah, I remember those days. Yeah. Like a month ago. Those were the days. Alright, so let's do this again. So this should be... This is with the thing accurate. So let's see. Let it settle. Oh, I didn't copy over the shaders. Okay, I was shocked then. It was like the same. Hang on, let me copy over the shaders. It's gonna get false data then. I was like, it's just the same. Why is it telling me that it was bad? All right, so this should be slower because of the extra operation that we're doing. Okay, so let's run that again. And let's give this a run. Let's see where we're up to. Okay, so 800, 900. We're literally this. Are we still at the right shader? Hang on. If I turn off the, no, it's the what? I'm so confused. Turbo speed. You can, yeah, I'm supposed to see a slowdown here that's noticeable. But I don't. Oh, this is so annoying. So I'm almost ready to say that this is not an issue, but does this scale bad? Optimization on another level. Yeah, does this scale bad? I don't know. Maybe this is not a bottleneck at all, if that makes sense. Maybe I've got another bottleneck that's slowing things down. It's considerably slowing things down faster than that. So maybe, yeah. What I'm saying here is, you know, that's not right, but that's not gonna work. Okay, Des. Just for the people, we may have like y equals x slowdown, and that's what the every time we add a thing to the scene, it gets y slower. Oh, x, I guess I should say. But there's a possible like x to the power of 2 slowdown, right? That, yeah, ignore this bit. Yeah, this is slowing us down, but like this is way slowing us down way more. So I don't know. Oops, that was a nope, leave page, that's fine. I would like to do it on the CPU. Yeah, explaining Big O basically. I don't know if everyone knows the Big O notation, so you know, to the people who understand that, that might be an O of n slowdown, but we might have an O of n log n, or an n squared that slow down somewhere else, which is just keeping the frame rate down no matter what we do. I don't know. Or maybe the graphics drivers have got so good at this that it's just not an issue anymore. Because when was this written? Like this article. When was this article written? This was written at least 9 years ago. And there's probably a... Maybe it's just not an issue anymore, you know? Sometimes things say that this is slow, but 9 years ago that was slow, and now it's like, doesn't matter. I don't know. I really don't know. I wouldn't even know where to start with calculating Big O for shaders. Ah, it's just... Yeah, it's the same principles, but it's just distributive computing kind of things. In the story, I think it is somewhat... I think it's completely different hardware. Yeah. I would have to ask online. I think what I might do is just quickly... This is a question for like other programmers to know. Like, is inverting a matrix, a 4x4 matrix on the GPU slow still? If you do it on a vertex shader, I don't know. I mean, 2000. Really? The 2060 GPUs don't have RT cores. I thought all 20 series have some RT cores. Or I could be wrong with that. I actually don't know. That's surprising, actually. Okay. Oh, okay, fine. Let's just move on. Let's just move on. What I'm going to do is just clean up, and what we're going to do is just go back to reading about lighting. Because, yeah, this is... this didn't work at all. This is not correct, so I just need to delete some code. The idea was there, but I realized that I was doing them wrong. I'll think about it. I think what I need to do is simplify in the long run. This... what I need to do in the long run, which I might like take aside to do because it is important, is this material buffer, which with all the materials in, is kind of the same as this positional buffer, right? With positional data in. Just so people are aware, when I say positional and material buffer, they are the same. On the GPU doesn't know what the hell I'm talking about when I say it only understands the word buffer. So I can put anything in here, and I can put anything in here. It's just the access, the way we're accessing these is different. And I don't know, it just feels like sorry, that's not true. They have 30 cores, but it's the first card to have it was in like 2018, yeah. That makes sense. That's what I thought. That's what I thought. I thought, yeah. The 10 series graphics cards didn't have them, and the 20s did. And the 16s didn't. Which were like this weird hybrid between the 20 and the 10s. Right, okay. What are we going to do? What are we going to do? So what I'm saying here is the material buffers, right, and the positional buffers are basically... They're trying to do the same thing. We have a material based on a submesh. Now, should we have position per submesh? Probably not. So that's the issue here, right? That's the issue I'm having. But the thing is, some of this stuff should not be per submesh. Like, or maybe it should be. Hang on, let me think. If I have a submesh and the position is different. Yeah, okay, that's okay. That makes things tricky. This is why it's so okay. So we shouldn't have this anyway. Okay, so let's get rid of this. That was a bad idea. Because submeshes probably can have different positions. So a submesh is just like a different piece of a model that has different materials. So if we look at like this bin, for example. Okay, it's a bit further up than I thought. Okay, a lot further up than I thought. There is a bin here. Like these have different materials on. And sometimes you need to render them separately to render them with their own material. But yeah, let's scroll down. Right to where we were. So what I'm trying to work out now this works, then I'm happy. I'm happy now. I'm happy. But what I was doing, I think, was a bad idea. Combining model, which could have a different setup per submesh, minus the position. It's not the same position wise. Programming's hard, guys. I tell you, it's fun but difficult. Who would have thought? The guy who decided to make a game engine in Vulkan is shocked that programming is difficult. Let's go through these. Okay, pad. Okay, that's the slang version, which we're not using. Get rid of this. And let's run that again. Yeah, Vulkan is difficult. Where do you get the inverse matrix for models? Because it needs to be in model space, and I need to transform the... okay, so there's a bunch of stuff I need to get rid of. Oh, I need to get rid of this as well. Hang on. Let me... It doesn't matter if it's the model or the inverse model. I'll show you. I promise this will... Well, I promise. We'll test what you said there, Mohammed. By the way, does Raylib have a Vulkan backend, or is it still OpenGL? I actually don't know. I've heard people telling me it's still OpenGL. I don't use Raylib. So let's bring back the logging and all the error checking, which is important. When I'm actively developing, I am going to also start the music again. I feel like a bit of a change, so instead of Dark Souls, let's go with, let's pause this for a minute. What should we go with? Just stick on in the background. It's got to be video game related, unfortunately. Due to the fact that, yeah, everything gets copyright claimed to oblivion. I'm going to go with my playlist that I have called All Music, which, in theory... allows me to play cool music. From various video games. Makes sense. It's really smart to use that, by the way. Raylib, if that's your goal, 100%. Okay, so let's test what Mohammed has been claiming, that we don't need a inverse model matrix to get the normal matrix in model space. So that's quite easy to check. Once I've removed everything and everything compiles. So yeah, we have to deal with that. Because that would be nice. That would mean yeah, everything's a bit simple. We can actually remove something from the shaders, and we have less data being passed from thing to thing. So yes, that would be good if we could do that. All right. All right, cool. Okay, so to verify this works, this is what it needs to look like. This is the correct scene, where everything's lit from one direction and everything's dark from another direction. That's correct. So if it's not like that, then the lighting geometry, sorry, the normal matrix for our thing is bad, right? Am I allocating more memory? It's now at 1.9 all of a sudden. Yeah, so let's get rid of this. There's a couple of things I need to remove to reduce that down again. Hang on, I just got to clean some stuff up if it's not. Yeah, okay, so... Okay. Let's just run that again to make sure there's no compilation errors from that deletion. Alright, yeah, we'll worry about that later then. Okay, cool. Let's close that. Okay, so we don't need the inverse model matrix. So let's not use it. Let's use the model matrix. Multiply that by the normals. Throw away the translation component. Yeah, that's the problem. Everything's the wrong way around. And you may think, okay, let's do this. Hang on. So this is the matrix applied with the position, right? So we're not doing this one. We're just doing this one, which is just both of them applied together. Oh, hang on. Did I get that right? Yeah, okay, no, I did. Okay. Oh, hang on. Oops, what am I doing? There we go. That actually is... looks correct to me. It's just reversed. Okay. Oh my goodness, that's so loud. That's blasted my ears off. Yeah, no, I think I got it right afterwards. Yeah, that has the directional line in. Correct. And if I turn around, there we go. So thanks for Mohammed. That's actually really useful. That's actually completely trivialized my problem. Look at that. Oops. So I need. Like, let's not I don't know how fast versus pre-computing things are, but I feel like doing a multiplication 3 times is getting overboard here. So so I'm gonna do mat force, and let's call this model position. Right, so instead of doing this twice in 3 different places, we can do this, we can do this, and this, and it looks like, oh yeah, it doesn't like. I'm getting too used to C++. There we go. Yeah, it's just backwards, which is fine. It doesn't matter at all which way the directional light is facing, relative to the normals. I don't think anyway. Yeah. Let me just compare them again. So let's see. If I take... let me just play around with this for a minute. Could you try asking an AI for pointers? Unless you're strictly against AI. I'm not really a fan of AI, and also it's not that good at this kind of stuff. Unless it's like really straightforward. So this might be what it's really good at. This might be like a big straightforward thing, right? Test. So what was the code? I can't even remember now. So we want to transpose. Oh, I can't remember. Let me look this up. Learn. AI is good at maths, in my opinion. It's not bad at maths. Well, I don't know what it's good at, to be honest. I don't really use it, but it's not that good at graphics programming. Where was it? This one. Let's see. This is what I was after. Thank you. So I'm just going to compare them, okay? It's I'm not saying anything's wrong or right yet. Right, V normal I think is the thing I care about. Yes. This is just then equal to test. This is just here to test. And we're going to take in this model position thing. Paste this in here and go. Yeah, it's not like good at Vulkan, for example. Oh, I'm an idiot. Yeah, I did that completely wrong. Apologies. So let's just compare the difference. I just want to see the difference. Yeah, I don't think it's any different. Actually, it's exactly the same. Fantastic, fantastic. Okay, cool. Thank you for that, Mohammed. MVP of the stream, I think. Yeah. Cool. Because that is a big pain in the neck. Yeah, so if you look at it again, it's just the other way around. Or is it? I can't even remember. But no, this is directional light. It's exactly what I need. Cool. Right. One step in the right direction. Okay, let's go back to studying lighting. Now we can actually do it because we've got our normals correctly aligned. It'll be good at this stuff, by the way. It's not like AI would have scraped all this off the internet and used it in its training data. I'm not saying it's going to be bad at this specific stuff, but it's going to get worse as you get more advanced. And if you're not leveling up your skills as you get better, as you progress through harder material, AI is going to fall off bad, and then you're going to be left in the mud, basically. So yeah. Right, so I need to change some of this to studying. Do you mind me editing something real quick? So this is toggle track. It's like allows me to edit stuff. I kind of want to add this to a different tag because that's what I did. I just developed the whole time. Anyway, now we can do this. Fantastic. I'm not the strongest. I'm the weakest when it comes to lighting and graphic and this type of graphics. So I'm leveling myself up so we can get like a nice game going. Which is right now why I'm very grateful for people who are like catching my mistakes. Anyway, right, fantastic. That only took forever. Okay, so I think this is spotlight, right? Oh. A punctual light. Yeah, what does that mean? I've tried multiple times, but I can't ever do it. I just do whatever comes to mind and give at any given moment. Makes sense, yeah? It's, well, it just takes patience and perseverance, you know. But that's hard to do. Easy for me to say, you know. All you have to do is work hard and be successful. Yeah. All you have to do to be rich is get money. Duh. You know. It's like that kind of silly advice, right? Anyway, our engine will support 2 types of punctual lights, commonly found in most, if not all, rendering engines: point lights and spotlights. Right, these types of lights are traditionally physically inaccurate for 2 reasons. They are truly punctual and infinitesimally small. They do not follow the inverse square law. See, okay, so spotlights and punctual lights don't follow the inverse square law. Wait, did I make a note on this? Hang on. Alright, it doesn't matter. We can do it. I can do it later. Or and can be truly infinitesimally small. Okay, so the first issue we can address with area lights, but given the cheap nature of punctual lights, it is deemed practical to use infinitesimally small punctual lights whenever possible. Okay, if you care about performance. For instance, yesterday I was working on my own space game. Oh, cool. I've been working and learning about ECS using Python. Yeah, it's that sounds really fun actually. I hope it's going well. But you know, sometimes having something organized in your mind where you can just like, I don't know, a follow-up thing. I'm kind of the same, to be honest. It's good to use either infinitesimally small punctual lights. Okay, the second issue is easy to fix. We're given punctual light, the perceived intensity decreases proportional to the distance from the viewer, or more precisely, the light receptor. Okay, we can solve the second issue. Oops. Issue with the thing is, Python's type system is a bit too limited, so patterns like ECS cannot be easily expressed in this language. Oh, I see. Without some weird workaround. Ah, right, I see. So that's gonna be, yeah, it's gonna be tough. Well, you know, you can always just not use an ECS. You can just use classes and just have the life components and all that hard coded in. It'll make looping through them a bit more difficult, but it's just, maybe it's another option. For instance, I've learned that there's things called existential generic types that only Rust and Haskell implement. Oh, I didn't know about that. Yeah, we have auto, I guess, but I don't know. C++ and C are a strongly typed language, which I really love. It's actually one of the best parts of well, it's one of the big W's of compiled languages, is to have strongly typed types. Anyway, we can solve the second issue by making sure the inverse square law has the term E in the equation. Right, I'm going to write the equations down because it's just easier. So, okay, that was a fail. This one. Okay, let's throw this in here. Seen this before? Just makes things easier. And 57. Oh. Okay, so using that, we express this idea with this equation. Let's go. Oh, hang on, let me just copy this out, otherwise it's going to be... okay. Yeah, this is going to take forever to type out. And we can do the n.l ourselves, which is nice. So, c \c dot l n. So when I do point lights, is that something I'm doing? That's the question. I over d to the power of 2, and then c dot n l. It's basically what Rust traits do. I see. Something like get even number. Right, I see, okay. I just use arrays in a no. Makes sense though. The caller knows this return type something. Right, yeah, thanks for explaining that. That's actually kind of that was easy to understand. Difference between a point light and a spotlight. Lies in how E... I'm gonna write this out. E is computed. Nice, okay. And in particular, how luminous intensity I is computed from the luminous power phi. Doesn't C++ doesn't have a native way to do this, I think. I should investigate later though, but I think you could do it with concepts. Not entirely sure. Concepts are ways to limit the amount, limit the template types that you can pass in. But I'm not entirely sure the just getting an iterator returned like that. I'm not entirely sure the syntax there for Rust, honestly. If that's a return type, I think you can return an iterator of a generic type and enforce a type to that iterator. That's been in C++ for a long time, but that might be not what you're doing there. I'm not entirely sure because I don't know the syntax. Yeah, it's one of those things. You can do it in most languages. Oh, is it just a template idea? Yeah, with a enforced type. Yeah, if you look at the array class in C++, that does that with 2 types. Anyway, point light is defined only by its position in space. Yes. Defined only by its position in space. Okay. The interaction, figure 36, interaction between a point light and a surface, the attenuation only depends on the distance of the light. Very good. Okay, so the luminous power of a point light is calculated by integrating the luminous intensity over the light's solid angle, as shown in equation integrating over the the luminous intensity can easily be derived from the luminous luminous power. Right. Okay, so by simply substituting I in equation 57 and E in 55, we can formulate the luminous equation of a point light as a function of the luminous power. The caller knows this return type, some type that satisfies this range concept. So you can do that with generics, I see. Yeah, Mabdo's pretty in Zig. He's doing great with it. I don't understand what I just read. The luminous power, which is because I've been developing for hours instead of doing this. What's the luminous power again? Luminous intensity, luminous efficacy, luminous efficiency, radiant power, the luminance. Okay, so luminous power is just lumens. Okay, fantastic. Okay, so lumens phi of a point light is calculated by integrating the luminous intensity, which is different again, over the light's solid angle. There's no easy printf function. Yeah, it's pretty It's too explicit. Yes, we've got to make sure we can print everything. Okay, so right, let me oops, look at my notes again. Luminous intensity, which is I. I'm gonna grab all that. And it's gonna have a bunch of stuff in it. Get rid of this. Okay, so over the solid. Okay, so got that bit done, and over lights, solid angle. What is this? Oh, sorry, I've gone too far down. Okay, so shown here. Okay, so let's get this in. Grab all this. Now, I'm probably not gonna roll this. So that is the oh, I see. Okay. That all simplifies to that. Are you kidding me? Phi over okay, so phi over pi for okay, so this way. Okay, let me pass through this a bit. Okay, so theta. So d theta d right, okay, so you have 2 pi over d theta and d phi. What is this? Yes, it is d phi. Okay, it's d phi. Which is equal to 4 pi times by the luminous intensity twice. Okay. Which we all know what's these backslashes for? Right, okay, let me oh, I didn't see the difference. Okay. It wanted to do this separately, which I'm going to do separately then. I was a bit confused, to be honest. Yeah, because now it wanted to do this. Alright, cool. I was wondering why it's double I. It was kind of confusing. Okay, so I is equal to... Isn't that just what I is equal to into general? Oh, what are you doing there? You doing some file copy stuff? I'm not entirely sure what you're doing there, but yeah, I don't know if it's outdated or not. But anyway, okay, so it's just phi, which is the intensity, 4 pi 2, which is the direction. Distance even. Okay, so d is distance. Let's write that down. So in this case, d is distance. We got a double integral here, but we got like a lot of. So the lumens is equal to. Huh. I don't understand this equals phi. Because if we equals phi and we also equal 4 pi over I, and then that I equals pi, phi over 4 pi. How does that make sense if we also if these two values equal the same thing, you know? Also, Zig compiles C better than Clang does. What? You can use C libraries anyway. Using Zig as a compiler is wild. Yeah, that's wild. Just checking something real quick. Okay. As a C compiler. Yes. No, I did get what you're saying. Yeah, using it as a C compiler. Okay, D is distance. I'm going to split this up. This is all kind of messed up, I think. I don't exactly know what it's talking about. Like, what is going on? Okay, so... do I have an equation that tells me that lumens equals this? Oh yeah, about C++ existential typing, I was right. You can do it. Templates. Oh, that's what you're trying to do. Yeah, I think concepts are 20, right? C++ 20. Yeah. Yeah, that. Now I understand what you're trying to do. Same as whatever, right? It's the important part. It should work with lots of error, lots of anguish, maybe. Anyway, integral. So as shown in, okay, let's read this. The luminous power of a point light is calculated by integrating the lumen intensity I over the light's solid angle. Okay. Oh, this no. This makes total sense, right? Because if I think this is super stupid of me. Let me bear with me just a moment. I think I've just been an idiot with my algebra. If I literally have what? Let's go with white. What is it? Try and draw the symbol properly. The equal to what? Four pi lumen intensity, then you could literally just take, just divide by 4 pi on both sides of the equation. Oops. Yeah, so that would be what? That would be... Alright, that's what I was going... I don't know why that would confuse me. Yeah. Okay, sorry about that, guys. That was a obvious bit of algebra there. Yeah, so that cancels and that becomes 4 of a thingy. Yeah. Yeah, C++ is fun still, I think. I just ignore like almost all the features and just kind of code like it's 1999 or something. With a few niggles about things that I like here and there. Maddo, is it easier to code in Zig when it comes to Vulkan? I actually haven't asked. You seem to be having a better time with Zig. You don't have to apologize. I've been watching three parts of your lighting equation, and I understand nothing what you're doing. Okay, fair enough. Yeah. Yeah, I feel like what I'm doing is like super basic and everyone knows what I'm doing. I don't know. Right, I'm gonna write this down. So it's just a disconnection I think that I got that was kind of confusing me. So the lumen intensity is equal to the lumen power over 1 over 4. I did it again, 4 pi. C++, yes, I'm coding C++. I'm coding C++, exactly. I take some of the features from the standard that I like and then abandon the rest. Because my goodness, you can make C++ look like a... Okay, where am I going here? Oh, Obsidian. I literally want to make notes. Okay, so by throwing... remember here, we are trying to add lighting to our BRDF by multiplying the lumen intensity, the luminous intensity, intensity luminous intensity. So with that in mind, we can throw in our lighting equation plus BRDF plus the direction of the light. Alright. So, I'm going to write this out because it's kind of useful. Just to kind of get in my head. So, it's all starting to like come together a bit. So this is the BRDF. BRDF V, comma L. And this is a frac. And this is phi, which is the lumen power. And this is 4/pi. You don't get to do that very often. Distance squared. Oops, not pip. And then left. Oops, not that. That, right? And right. That? Oops, that? No. How do you do these? Left this. Oh, okay. Wrong place. So cut and n c dot L. Fantastic. Okay, so this is not that complicated. That is literally what we've written in our shader, right? Literally, we've literally written that. So let's look at what we've written in our shader, and I'll show you exactly what that's trying to express. So in lumens, which is our power, which is our thingamajiggy, right? We have BRDF times by, okay, so we put light intensity. This is to be lumens, right? Lumens times by L dot lighting based on a normal, right? I can technically get rid of that. It doesn't really make any difference. So it's BRDF. That is that part. Now where's our obsidian notes? That is okay. That is FV. Okay, so that's our BRDF. We've written it like this. We just combine the. We've done the terms separately rather than combine them. Times by the lighting intensity, which is this. We've just decided to make it like this. Times by the normal direction. So, yeah, that's the point lights. Sorry, that's the directional light. But we can easily add other things if we just get the distance, not direction. So we just need intensity divided by 4 pi times by distance squared, and we get the distance via what is the distance? The distance is calculated by distance. So our distance is our this times by that. And this is us trying to do the spotlight in one go. Which is, I don't know why that's that complicated, but I guess the so that's the D value in this. That's D. That'd be the D squared. And yeah, there it is there. And yeah, I think this is just rearranged a little differently, but effectively it's that pi, 4 pi, and then lumens. How many lumens intensity? So how much you've sent in this thing. So that's the intensity, 1,500 lumens. I can transfer these concepts to a better language. Maybe I should use it and excuse the final functional language I've heard. I see, yeah. Oh, you gave your opinion. I think C++ is the only language where you can do absolutely everything in. I switched to Zig because of Andrew Kelly. Yep. And the foundation behind it, it's amazing. Yeah, it's 100% goated. He's a great fella. Great aspirational guy. Okay, so with that being said, I think I'm getting lighting in general right. I've got the general gist of lighting now. We are just solving this, and the lighting itself is this guy. It might be complicated, but it's still just this part of the function, n.l BRDF. What I don't know is he's not written any of the... Oh, he has. So... What is this? This is the implementation of punctual lights. Which one's spot? Get square, fall off, and entrainment. So this is the... What is this? This is I actually don't know. Okay, it's not too important. Right, let's get some water. It's all via integrating formula. That's why it looks so complicated, but it can be derived 100% just watching. It's really nice that I'm really nice. I feel like I'm starting to understand it in general. Finally. Okay, so we've done that. The spotlights. Let's keep going. So we have fixed a big issue in my engine. No, you can actually do lighting, which is lovely. Okay, a spotlight is defined by a position in space and a direction vector and 2 cone angles, theta inner and theta outer. Right, okay, so a spotlight. Let me just start the music again for our listening pleasure. Yes. No, I won't pick a piece of music while I'm here. Spotlight. Right, okay, let's go back to filament. Let's close this. I don't need it. A spotlight is defined by a position in space, a direction vector, and 2 cone angle. Oops. It depends on what you're trying to do. You're trying to make. It's all the first half of the book. Have you got a book? Oh, let's say theta. I'll just go inner. Which I'll do like that's exactly the same. Okay, so and outer. Okay, so which we can see in this, the 2 angles are used to define the angular fall off and attenuation of the spotlight. It's getting late. Okay, so the 2 angles are used to define so is this all so this is how spotlights work in Blender? Yeah, it must be exactly the same way. It's just how they resolve the BRDF is different for sure. Yeah, because that's it there. That's literally the formula for it. That's a spotlight. Oh, do you mean spotlight or point light? Yeah, spotlight. It must be the same. Yeah, it must be the same. Of the spotlight. Right, sound. The light equation. The light evaluation function of a spotlight must therefore take into account both the inverse square law and the 2 angles to properly evaluate the illumination attunement. I keep saying attunement. You know what I mean. Okay, so the light equation by spotlight must take into account both the inverse square law and these 2 angles to properly evaluate luminance attenuation. Okay. let's just oh, what am I doing? Just grab that. Literally right there. Oh, that is right. Okay, so I do like this picture, so I'm going to throw it in. Cool. Avoid macros, macros of the devil. Really? I think so long as you avoid template metaprogramming, like the plague in C++, and then don't go too wild with iterators in C++. Yeah, see, I agree. I agree. Generally speaking, yeah. I like to go even further than that. With cutting off features in C++. So there's Lumon in top. Oh, I see. It's the same deal again. Right. Okay. So equation 60 describes how the luminous power of the spotlight can be calculated in a similar fashion to the point lights using the outer theta angle. The outer angle of a spotlight. The outer angle of the spotlight cone in range 0 to pi. Okay, so just like with backslash theta underscore outer. I have to go, Escape Point. Always a pleasure catching your streams. Thank you very much for everything. Yeah, thank you very much for turning up, and I'm glad I was able to make a positive impact on with my streams. Yeah, I'll see you on another one, hopefully. Yeah, have a good rest of the day, dude. Yeah, it's great having you here. Yeah, Mabdo's been learning Vulkan, and he's getting good. He's getting good. He's just unlocked textures, so he's rendered a textured model, which is it's always inspiring to see that the progression. So yeah. So anyone who is watching, if you are considering learning Vulkan, this maths may be off-putting, but just realize I'm like trying to learn how. I'm gonna just do that because it's easier. How light works, which is different from like learning Vulkan, right? I think it's not as difficult as it's makes out. Vulkan isn't as hard as it's made out to be, especially with Vulkan 1.3. It was harder back in the day with render passes, but it has got simpler and easier to handle. I kind of wrote this all silly. Spotlight. Yes, Vulkan is not hard, but it's extremely verbose. Yes, and it wants you to do things in the Vulkan way sometimes. And it's kind of, if you've learned DirectX, you can end up how spotlight theory. You can end up kind of annoyed by it. Light theory. You can work this equation out with the outer angle of the spotlight cone range in the domain of this. Fantastic. Yeah, that's the off-putting thing about it. I wish they had just a bit more way of abstraction of for simpler things. Yeah, it's not the perfect API. I wouldn't say that. It's just like if you want to move with the times and be cross-platform, that is the way you want to be doing it, in my opinion. Again, it's just an opinion. But let's go to this. I think graphics programming in general is hard. So sometimes the stuff that gets thrown on Vulkan is sometimes just hardware limitations and like vendor stuff, plus graphics programming being a pain in the neck, as you can probably make out by this this stream, which has been basically no Vulkan at all, and mostly graphics theory, plus me working out basic things that I didn't realize. That you could make this, you could make all the mistakes I've made today and correct the things I've corrected in OpenGL and DirectX. While this formulation is physically correct, it makes Spotlight a little difficult to use. Changing the outer angle of the cone, the illumination with changing the outer angle of the cone changes the illumination levels. You see, shows the same scene lit by a spotlight with an outer angle of 55 degrees, and then the outer angle of 15 degrees. Observe how the illumination level increases with the cone aperture decreases. Right, yeah. So, with this equation, as you decrease the outer cone aperture, the lumen intensity, illumination level increases. It's got a bit quiet. Let's just check the audio levels for you guys. How's that? I don't think that's too bad, right? Just barely hear any of the music. Okay, so where's the thing that I care about? Lumen level increases the cone aperture. Right, so oops, yeah, I can throw that in there. Morning, Mika. How you doing, dude? I hope you had a good night's sleep. Good to see you. Look at that. I'm working through the whole night, and you're sleeping the whole night. No, it's obviously. No. Hope you had a great day. Great night's sleep though. Man, I'm getting tired. The coupling, illumination, and the outer cone means that an artist cannot tweak the influence of the cone spotlight without also changing the perceived illumination. It therefore makes sense to provide artists with a parameter to disable this coupling. Equation 61 shows how to formulate the illumination power for this purpose. Right, so this new formulation to compute the lumen's intensity, excuse me. Oh, Excuse me. Yeah, that's choking. With the new formulation, I'm fine. It's just talking so much, I think. With the formulation to compute the luminous intensity, the test scene of figure 40 exhibits similar illumination levels with both cone apertures. Okay, to fix this, you'll want to add this to the equation. So phi backslash vi equals pi, excuse me, I, or because we know some algebra from high school, I might have actually, with my high school education, been able to work this out. You know, with none of the maths that I ever learned after school. Yeah, I think this is simple enough that I probably could have worked that out. Obviously, I know more maths now. That's what I'm trying to say. Like, right. So, this new formulation can be considered physically based if this if the spot's reflector is replaced with a matte diffuse mask that absorbs light perfectly. Huh. The spot's light evaluate function can be expressed in two ways: light absorber, light reflector. The lambda L in both 62 and 63. Did you learn calculus in high school? No, I did not. I barely learned any maths at all. They put me in the basically the bottom sets in pretty much everything in school. So I had to teach myself after the fact. So I could basically do this. This is the stuff that I could do back in high school. I couldn't tell you what this was. I couldn't tell you that we're integrating I over both over 2 pi in every direction with d theta, and then outer with d phi, right? Is equal to I didn't even know what pi was when I left school. Well, I knew what it was, but I didn't know what to do with it. I just heard it. I've heard it before. I was in a big enough school that if you were considered, because they cared more about you matching your expected grades back then. So if your expected grade was really low, they didn't care at all. As long as you met your so they put your expected grades really low if you were a terrible student. And yeah, yeah, that's just how it was. Yeah, there's a whole I could go into a whole story about that, but yeah, I was basically my expected grades in every class, just to put it in perspective, was an E, which is 1 grade above a fail, a complete fail. I couldn't even answer any of the questions. So that's that's how that went. Yeah, that's no way of educating someone. Yeah, it's so literally I didn't know literally anything when it comes to maths. You should expect students excellence. Yeah, unless you have genuine cognitive deficiency. Yeah, and I generally don't. The only thing I have is dyslexia. That did obviously not help at all, but it wasn't to the point where I was should have been expected an E in every single class which, like I said, was just one above a fail. So yeah, C was considered a pass, but F was the real fail. But if you didn't get anything above a C in the UK, back when I was in school, like it was considered a fail. Technically, you got a pass, but it was like lower grade pass that no one cared about. That's how it was when I was in school. Now it's numbers. It's like 1 is the worst, I think, and 9 is the best. They've changed it recently. I have younger brothers and sisters in a school, so they don't have A, B, C, D, and all that. If the spot well, the only thing to do now after that is if you didn't do well in school, it's just to prove them wrong. That's it. Just gotta keep climbing. That's how it is. No point crying about it, you know. Just gotta do better than they expected and beyond. It's the leave them in the dust mentality, you know, rather than get revenge on them or anything like that. Call them out on social media or anything. Leave them in the dust, bro. Okay, so we have two. Okay, so we have two things. Okay, so we have a. So there are two. Equations here. One with and without a light. Oh, one with a light absorber. And one with a light, reflector. I was a bad student in school. I never quite finished high school, but I managed to get into college anyway. And last month I got my master's degree in philosophy there. No, that's really sick. I mean, well done, dude. That's honestly real. That's a real achievement. That just shows you, like, sometimes you're just left out to fail, and there's not really much you can do about it until later on. And it looks like you did the same thing. You left them in the dust. You know, you've got your own thing. You've got your philosophy masters. I'm sure you can tell me a lot about things that I don't know. Yeah. So yeah, that's a W and a half, that, bro. Okay, so phi, and so we have pi, d, d. Oh, why am I writing this out? I could just literally take the code. Not the code, the LaTeX. I don't need to be a LaTeX programmer. You know what I mean? I could just do that. Ta-da! C dot. So n dot L. It's the same old, same old. L, n. Oops, n first. Not that it matters. It's a scalar. N dot L, but you know, gotta be careful with cross products, for example, or a wedge product. If you use trivectors or bivectors in the wrong order. Anyways, so this is with a light absorber. And this is without. So we've got I don't know what these mean, though. That's the question. That this is with a light. I think what I should work out here is what it means by light. I think a lot of this stuff comes up in the actual code here. Yeah, because we have BRDF, intensity achievement, n.f. So this is, it looks like for, as far as I can see, this is for not a point light. I think the point light is too easy to do. So the attenuation fall off. So okay, so this is just I can match the maths with this, I think, in the end, but we haven't got there yet. I see. So we need a proper inverse square fall off of the. Okay, so we need. That's why we have more code. I was thinking, like, why is there so much code here for this one light? But it's got the it's got two different lights here. Sorry, it's got it's got this extra like light fall off thing over time, I think. Right. Okay. So that's good to know. Anyway, that's enough looking ahead. We could. I should just do this. As far as I'm aware, this is the. Isn't this the same thing? Oh no, it's not. Okay. So 2 pi 1 cosine theta outer, and this is d squared. Fantastic. Okay. I think no, we don't have repeating music. This is just. Sometimes the YouTube playlists repeat, and I sometimes get paranoid. So anyway, that we're just listening to the same song. C dot. N dot L. Right. Okay. Cool. Yeah. What is this lambda? The term lambda L is expressed in the expression. That and that is the angle attunement factor. Right, okay, so lambda, okay, that's good. At least it explained it. The lambda term lambda L in equations above is the spots lights angle attune Asian factor in cool. Loud LaTeX is incredible for this type of stuff. Holy, I'm so glad it exists. This website, fortunately, I was copying. I was learning like ray tracing, like offline ray tracing, recently. Turns out the book was called Physically Based Rendering, and I was like, oh, I get to learn physically based rendering. No, it turns out I was learning offline path tracing, which is fine. So I had to stop that book in the end because it wasn't relevant to what we were doing. But despite that, it had. That's where I learned LaTeX, and that didn't have. I wasn't able to copy that. The reason I'm bringing it up is because I wasn't able to copy this out. But this does. So this is like this website is super good. that we're able to copy out the latex attenuation function. Fantastic. Okay. So the spot, light, angle, attenuation factor. Cool. And if I scroll down to here, we have the attenuation. Okay, so that's that function. That's that one. Fantastic. Okay. Then we have this fall off, which I believe is this one. And we just add them together. And then it looks like attenuation, light intensity, light color. Nice. Yeah, that's a good point. Actually, I want to try light color just real quick. If it's that simple. Wrong shader. I haven't done light color in ages, actually. Alright, so just make sure this is going to work. I'm just going to make it all Vec 3. No, not 29. 3. It's extremely cool thing to be learning about. Maybe one day I will be disciplined enough. Oh, yeah, anyone could do this. I mean, you got to remember, like what I told you before. You know, the teachers in school thought I was dumb. You know, they didn't think I'd be able to do anything. So, you know, if I can do something, then I'm just gonna check out like a random value. I have no idea what this is, what color this is gonna be. I just want to see like a cool color. Like you can do this, dude. You got a master's in philosophy, dude. You're very disciplined. Oh, I'm in release. I need to be in debug. Not that it matters too much, but okay, right. Let's give this a quick whirl. See what the colors are. Have I disabled the? I should have enabled them. Thank goodness. Cool. Let's see what happens. Oh. What? Oh, okay. Yes. Okay, so we got like a horrible green. Okay, cool. Like a green radioactive sun. There we go. But it'd be nice to match the background, you see. If I, obviously white is pretty accurate, but you know, a nice orange. Now all the rocks look moldy or radioactive. I don't quite know. The Matrix has you yet. You're breaking down. There we go. Cool. Yeah, I'm learning so much. It's so fun. It feels so good that I've, you know, studied. And people have helped so much, which is fantastic. Alright, after everything gone green, it is 5 o'clock. I'm going to share my Discord server for anyone who wants to join. Feel free to join and, you know, chill. Just have to follow the rules and stuff. That's it. So I'll just throw that in there for you. Yeah. Anyone's welcome at any level. Whether you've been programming for 5 minutes or 500 years. You know, you're all welcome in. And yes, I'm still going to end it here. I just want to say thank you for everyone who's commented on this stream, liked and subscribed, or has stayed subscribed. Honestly, it's very much appreciated. Thank you for putting up with my silliness and progression through making things work and that. You're all very much only 2,000 years. Yes, you're very much appreciated. And yes, I'll leave you here, guys, and have a good rest of the day, everyone. I hope you all have a fantastic rest of the day. So yeah, all right, bye for now. See you in the next one. All right, bye, guys.